The goal of this course is to bring you to a useful level of comfort with the Java programming language. I'm assuming that you're reasonably familiar with programming in some other language, but I'm deliberately not assuming that you're familiar with object-oriented languages. It's not a problem if you are, but I wanted to avoid locking folks out over that. A lot of people have found that the transition from regular or procedural languages to object-oriented languages can be a bit tricky, but that's something I've spent most of the last 20 years learning to help with. So, why would you want to learn Java? Well, it's a mainstream language that accounts for a large proportion of new server-side application code. So there's a significant chance that the job you want requires, or at least would benefit from, Java skills. Java is a robust, well-supported language. It has libraries covering a wide variety of functional areas, including graphical user interfaces, distributed computing and web services, high-precision mathematics like you might need for scientific applications, high-performance I/O and multi-threading like you'd need for high-throughput server systems. Java also provides real-time options that can be used for control systems. So for example, if you want to make robots, Java is still an excellent language choice. Of course, these examples are just a few of the high spots. If you include third-party and open source code, there are Java libraries for almost anything you can think of. Java also has extensive infrastructure support, with many popular frameworks built around it. So, for example, you might find yourself working on a project that uses the Spring framework, or perhaps Java EE, the Enterprise Edition. This course will take you through the first steps of becoming a skilled Java programmer. There's a lot to learn about Java, and of course a relatively short course like this can't cover all of it. But I will give you a great start, and you'll be writing your own code comfortably when you're finished. The course is composed of 7 lessons. In Lesson 1, Learning Java, we'll look at the tools you'll need, like the compiler and the development environment. We'll get them installed on your computer. And once they're ready, we'll create and run the traditional first program, Hello World. In Lesson 2, Procedural Java, we'll look at the foundation pieces of the language that are familiar to all programmers, including those with a procedural background. You'll learn to use variables, create expressions, write code for conditions and loops. Next, in Lesson 3, From Structures to Objects, we'll look at handling complex data, and we'll work from the notion of structured data types up to the introduction of the essentials of objects, what it is that makes them different from structures, and why that's a good thing. After that, in Lesson 4, More About Objects, we'll move your understanding of object-oriented concepts and the language features in Java that support them forward. We'll introduce the crucial concept of generalization, along with inheritance, abstract classes, and interfaces. By this point, you'll have a pretty good grip on a large part of the Java programming language and the concepts that work with it. So in Lesson 5, Java I/O libraries and exceptions, we can start to put this all to work. You'll learn to work with files for input and output, and we'll introduce Java's library documentation, and then add to your language skills by introducing Java's exception mechanism. In Lesson 6, Creating a User Interface, you'll discover the essentials of the Swing Graphical User Interface library. You'll learn to put components on the screen and write code that causes things to happen when the user interacts with those components. Finally, in Lesson 7, Creating a Chat Program, we'll build a real program that puts all these things together. You'll create a networking chat application. By the time we're finished, you'll have a solid foundation of Java programming, and you'll be ready to move your career to the next level. Let's get started. In our first lesson, we'll get your computer set up with the tools you'll need to work through the rest of the course. You'll need a Java development kit, and you'll need something to write and test your programs in. That will be the NetBeans Integrated Development Environment, or IDE. Both of these are free downloads from Oracle. We'll first discover how to determine if you already have a Java development kit. Then we'll run through the installations of that and of NetBeans. When they're installed and working, then we'll prove the point by writing your first program. It won't do much. We want to keep it simple while we verify that everything is working as it should be. As you might expect, it will simply say, "Hello world." Welcome to Getting Started with Java. This course will take you through the first steps of a journey to becoming a skilled Java programmer. There's a lot to learn about Java, and this short introduction won't cover all of it, but it will give you a great start, and you'll be writing your own code comfortably when you're finished. So, why would you want to learn Java? Well, it's a mainstream language that accounts for a large proportion of new server-side application code, so there's a significant chance that the job you want requires Java skills. Java is a robust, well-supported language. It has libraries covering a wide variety of functional areas, including graphical user interfaces, distributed computing and web services, high-precision mathematics, such as would be required for scientific applications, high-performance I/O and multi-threading, like you'd need for creating high-throughput server systems. Java also provides real-time options that can be used for control systems. So if you want to make robots, Java is still an excellent language choice. Of course, these examples are just a few of the high spots. There are actually libraries covering almost anything you can think of. Java also has extensive infrastructure support, with many popular frameworks built around it. So, for example, you might find yourself working in a project that uses the Spring framework, or perhaps Java EE, the Enterprise Edition. All these and more require a knowledge of Java programming, and that starts right here. In this lesson, we're going to take a look at verifying that you have a Java development kit. There are two types of Java installation that can exist on a computer. The first one, and the one that we need, is a full Java development kit, or JDK. In a JDK, you have tools for both running programs and for writing them yourself. The other type of Java environment is intended just for end users who wish to run Java programs written by other people. This one is called a JRE, or Java Runtime Environment. The crucial difference is whether or not you have a compiler. Let's take a look at how you would make that determination. To do this, you need to bring up a command line tool. In a Windows environment, there is a command line tool called CMD, and you can run that from the Start menu. In here, in the Mac, we have a terminal, and to determine whether I have a Java installation, the first thing I need to type is Java -version. And that will tell me if the response comes back Java version and then some version number, then I at least have some level of Java installed on my machine. In this case, I have Java 1.6, and that's sufficient for our needs. If you have something newer than that with a higher number, 1.7 or so on, then that's fine too. Another possibility is that you might get a response that indicates that Java is not installed. That will be something like command not found. Assuming you do have a Java command available to you, the next command we need to verify is the javac command, and again we're going to type javac -version. Two things need to happen here. The first one is that we need to see that we get a javac response rather than a command not found. If the command is not found, then you have a JRE perhaps, but no JDK, and we need a full JDK. The second thing is that we need to be sure that we have the same version number for javac as we had for Java itself. If any of these things don't work out right, then we're going to need to download a Java development kit. To download a Java development kit, we need to take our browser and go to Oracle's website. Oracle, of course, is now the owner of Java, so we'll start by clicking on the Downloads link. From Downloads, fairly near the top of this page, you'll see under Browse by Category, Java. And within Java, what we need is Java SE. That stands for Standard Edition. So click on that link. We have a number of different versions and releases of Java to choose from. Choose the Java Platform Standard Edition and make sure you select a JDK. Click on the Download link, and that will take you to a page that you can choose which particular platform you're downloading it for. The first thing you'll have to do on this page is accept the license agreement. Then you can take a look at the available platform support files and decide which of these is most appropriate to your environment. So in my case, I'm running Mac OS X, and I would click on this version with the DMG package. For the Windows users, we have the exe files down here for 32 and 64-bit binaries. Download that file, run the install through your regular operating system commands, and Java will be up and running for you. And that's it. that should get a running version of the Java Development Kit on your machine. In this lesson, we're going to install NetBeans. NetBeans is the IDE that we will use for developing Java programs with. It's available as a free download, sponsored by Oracle, and after we've downloaded it, we will start it up, take a quick look at it, and create a minimum Java program just to make sure everything's working properly. So to download it, we will start by pointing our browser at netbeans.org. And we'll see that the home page for that project actually has a nice big orange download button ready for us to click on. When we click on this, we will see that the host has determined the operating system platform that we're going to run on, and assuming you're going to install it on the machine you're using to fetch it, then this is probably going to be correct. And it offers us a choice of different versions of NetBeans. The version of NetBeans that we want will be the one for Java SE. There are others that we could use, which include all the facilities we need, but they're significantly larger, and that's just unnecessary. So we then click on that, start our download. Should start automatically, as it says. If it doesn't, you can click here just to make sure. And once the download has completed, we will open it. And we will launch the program that we fetched. The installer is pretty simple. It will prompt us to approve of its license and give us a choice about where we install it. I'm simply going to accept the default locations for that, so no problem there. Of course, it will then want to prompt us for the privileges necessary to actually do the installation. And we'll find then it will write the files onto the disk, set up the configuration, and there's a little step right at the end of this where it says running package scripts that can take a significant amount of time. So just be patient and it should eventually finish. Might be a minute or two. So now the installation is complete. We can shut that down and then we can run the program. So we should find that it is installed under Applications. We'll look for NetBeans. There it is. And we'll start that. When it starts up, it always brings up this banner screen you'll get familiar with, and it tells you what its progress is, because it does take it a moment or two to get going. One of the other things that NetBeans will do as it starts up is to check for updates that have been made to the software since you last used it. So that's nice that it keeps itself up to date. When it starts for the first time, it will offer you this splash page, and it will also offer you the chance to install JUnit, which is a testing program. We're not going to use JUnit, so we'll press cancel for that, and then we'll get past the splash page by just clicking on that little box up there. In this lesson, we're going to create our first Java program. Launch the NetBeans IDE, then click on the box with the plus sign that has little help text that says New Project. Ensure that you have selected Java and Java Application, and then hit Next. We'll think of a name for our project. Good software engineering always has good names for things. Of course, our application is going to be very simple, so we'll just call it Hello World. We also need to come up with a name for the class that we're going to create. The class name is actually in two parts. The first part is called the package name, and the second part is actually the class name. You'll see these again inside the program in just a moment. Since we chose a project name of Hello World, it has given both the package and the class the same name, and that's fine for this because it's fairly meaningful for what we're going to do. Hit Finish. NetBeans builds the project directory, creates a folder for source packages within it, and then creates the package Hello World with the helloworld.java source file within it. In the editor window, which it also opens up at the same time, it brings up this helloworld.java program source file for editing. You'll notice the very first statement says package hello world. Packages in Java are a kind of namespace. They allow us to give short names to our classes, like Hello World, and not have to ask every other developer we ever work with whether we are treading on their toes and reusing a name that they might have used. As long as our package names are different, it won't matter. The package statement should be the first thing that occurs, other than comments, like these, inside our source file. The next thing is that we have this line that says public class hello world and ends with a curly brace. Curly braces show up all over the place in Java, just like a lot of other languages that came before it. Inside the class, we have this method declaration. If you like to think of a method as a kind of function or procedure, that's fine. Object-oriented languages use the term method, and there's a slight difference between a method and functions and procedures that you might have seen before. In this case, the method is labeled public static void main, and in the argument list we have string array args. This is all by convention. It must be a public method. It has to be static. The return type, that is to say the type of data returned by the method, is always void. That really means it doesn't return any data. The name of the method must be main. Everything, by the way, in Java is case sensitive, so this must all be lowercase. The arguments to the main method are an array, that's what the square brackets are for, of string being sequences of text characters. The only thing about this that can be changed is the fact that these are called args. That's a long-standing convention and there's really no reason to change it, but you could call it something else if you wanted. Then the body of the code that defines this method goes between the curly braces. Let's remove the comment line. The 2 forward slashes you see here are another form of comment delimiter. These ones say that from this point to the end of the line is a comment. These guys present multiple line comments. So we'll select the comment because we're going to delete it, and then we will say very simply system.out.println, and then we'll put parentheses on and then quotes, and inside the quotes we will say hello world, and then at the very end of the line we need a semicolon. This system.out.println is a little bit complicated and we're not going to explain that fully right now. As you can probably guess, what it does is to print its arguments out onto the console, and at the end of printing that argument it will put a new line character. So in our case we have the long-standing traditional message hello world, which of course is usually everybody's first program in a language that has curly braces in it like this. We can save the file with the icon up here in the top left corner. Click on that, and then we can run it using the green arrow key here. Notice it says run main project. When we run it, we get an output console window down here, and we see that it says hello world, which is the output we asked for, and then it finally says build successful. So there we go, our very first Java program, and a little bit of explanation as to what the various pieces mean.
Welcome back. Now that you've got the infrastructure configured and you've got a working compiler and environment you can actually experiment with Java with, we're going to move forward and look at writing more real code. Although Java is an object-oriented language, we're going to start from a foundation that doesn't require you to have prior understanding of object-oriented principles. Underneath even object-oriented programming languages, there are some common essentials that are what make up procedural programming languages. Things like sequence, running one instruction after another, iteration, running things in loops, and selection, being able to do something conditionally, for example in an if statement, so that under certain circumstances the program will do one thing, but under other circumstances it will do something else. All of these features are common to procedural languages and object-oriented languages. So we're going to start there so that no matter what your background, you can get to grips with this as quickly as possible. So the lessons that we'll look at will cover, in order, the basic mechanisms that Java uses for handling variables, and with it the idea that Java has of type. Java is a strongly typed language, and if you say something is a number, it's going to be a number. In fact, Java is even more specific than that. So we'll teach you about that.
Then we'll move on and look at operators, operators that will do things like addition and subtraction, and also comparison. Next, we'll move on and take a look at the conditional mechanisms that Java provides. Java provides if statements with else, and also a switch statement, which is sometimes referred to as a case statement. Either of these mechanisms can allow you to write code where under one set of conditions a particular course of action is taken, but under a different set of conditions something else is done. Next, we'll look at loops. Java has 3 different types of loops, and we'll look at all of them at least briefly so that you can make a good start using them. Of course, when you're working with loops, one of the data types that you're most likely to want to be addressing are called arrays, and Java provides arrays too, so we'll take a look at those following that. The final lesson in this particular part is going to look at what are called methods. If you're familiar with object-oriented terminology, you know what a method is. But if you're not, don't worry about it. It's just a fancy name for a procedure or a function, but in the context of an object-oriented system. At the end of this section, you will have learned quite a bit about the basic mechanisms that Java uses to build programs. And you'll be able to write some real code of your own, even if it isn't object-oriented yet. In this lesson, we're going to introduce some of the basic mechanisms of programming in Java. Object-oriented languages have a special way of breaking down large programs, but the elements that we break programs into, unsurprisingly these are called objects, are coded using the same procedural tools that are familiar from other languages. These tools are variables, looping and conditions, along with declaring and invoking methods. To introduce these, let's look at a simple example. This one is in the package temperature. The first thing is that Java programs generally start at a method called main, so this is where we're going to begin the program's execution. The very first thing it does is to declare a small array of temperatures. So temperatures refers to all of these values, and temperatures with a subscript on it in square brackets, which is what Java uses for accessing elements of arrays, will refer to one particular element of this. What we then do is to iterate over the elements of that array one at a time. All arrays start at the index 0 in Java, and they all know their length, and they actually have this variable called length. So in this case there are 4 elements, so temperatures.length will be 4, and as long as I is less than that, because these are obviously numbered 0, 1, 2, 3, then we can go and examine the temperature for that particular temperature. Examine temperature is a method. Method is the word that object-oriented programs use in place of function or procedure. This method is declared as returning void, which really means it doesn't return anything. That kind of makes it more of a procedure than a function. We pass in the temperature to it that we want it to look at. It then prints out a message that says temperature is temp Celsius, and then it goes on to call another method. This one is actually a function type method because it returns, up here is the definition of it, it returns an integer value. The integer value is computed based on the conversion for Celsius to Fahrenheit temperatures, and when it's done that computation, it returns that temperature. So here we now have another variable, again an integer type, a simple integer this time, that describes that Celsius temperature in Fahrenheit. So then it prints out the Fahrenheit temperature, and then it uses conditional statements, the if statements in Java. There are others, but this is one of them, to say if it's less than 45 degrees, that's chilly. If it's more than 80, then it's pretty warm, and otherwise that's nothing special. So it's a very simple little program. It's not wildly exciting for sure, but it's hard to be exciting in a very brief example. But it shows you the kinds of things that we're going to be looking at for the rest of this chapter. So to recap, we've taken a first look at the entry point for a Java program, how to declare variables and methods. Remember that's the name that OO languages use for functions and procedures. We've looked at arrays, loops, and conditional statements. But remember, it's okay to be a little fuzzy about much of what has happened here. This is just an introduction, an outline of where we're going next. The rest of this chapter's purpose is to lead you through these techniques in more detail. In this module, we're going to take a look at Java's variables. We'll look at the types of variables Java permits, how to declare them, We'll look at how to initialize them, in particular how we can define literal formats for them. We'll also take a quick look at the normal naming conventions that Java programmers will expect you to use. Let's start by creating a new project. We'll create a regular Java application. We'll call it variables. And then the first thing we'll do is to bring in a number of variable declarations so that we can look at the most common types. The format of a variable declaration is always essentially the same. We start with the type of the variable, then we have a name for the variable. Names should always be meaningful if at all possible. In this case, though, we don't actually have a purpose for this variable other than demonstration. So all I've done is call it a byte. So the name there, a byte, is reflective of the fact that this variable is a byte type. Then I chose to go straight into an assignment. I've got the literal value 127, which is a decimal number in this case. And a byte value is exactly that. It behaves like an 8-bit value. Other types that we can have in Java for numbers, we can have a short, which is essentially a 16-bit value, an int, which is like a 32-bit value, and a long, which is a 64-bit value. We don't actually have to initialize a variable the moment we declare it, although it's probably a good thing if you can, that way you won't forget. If we chose to, we could comment out the rest of this line, and as long as we complete the line with a semicolon, that would simply declare the variable, but then wouldn't do anything with it. So I'm going to leave that as a variable declaration with an assignment. Notice the naming convention for variables in Java is that we start with a lowercase letter, and then if we have a join in words, so in this case we're saying a byte, the start of the next or subsequent words, we actually use a capital letter. The literal formats we have here, if you simply go straight into the declaration of numbers, 127, then the number will normally be assumed to be decimal. But if you start with a leading 0, as in this case, then the number will be taken to be in base 8 or octal. In that case, of course, you can't have any digits that are greater than 7. We can also declare literals in hexadecimal. So in this case, with the leading 0x, I can start using hexadecimal digits, which of course are 0 through 9 and then A through F. In addition to integer types, we also have floating point numbers in Java. And the floating point numbers that we have are the float type and the double type. Float will actually use 32 bits for storage and double will use 64 bits for storage. So double is significantly wider range and higher precision, but float is often enough. The literal formats for floating point types are basically anything that has a decimal point in it, or anything that has an exponent expression, something like that, e plus 99. And by default, if you simply have a number of this sort, it will be assumed to be a double value. If you want to explicitly say that this value is a float type, the smaller type, then you can use an F suffix. Actually, uppercase or lowercase are both acceptable, but it's usual to use uppercase letters in these situations. You can also describe a double explicitly with a D suffix. Again, capital would be normal, but this of course is unnecessary since the default is double. Java also provides a variable type for characters. Character being a single piece of text. Characters are actually represented as 16-bit unsigned numbers, and they are represented using the Unicode character formats. That means that Java can work quite comfortably in most languages around the globe, not just in languages that use a Roman or ASCII alphabet. The character type is declared as type char, and the normal format for the literal is to use single quotation marks, not the double quotes. They're used for string types. And then to specify the character inside of it. So here we have the character uppercase A. There are actually other formats for character literals as well. Because we might be representing characters that are not available to us on our keyboard if we're dealing with a Unicode environment, we can actually explicitly state, in this case, I want the character represented by the Unicode character 41 hexadecimal. So this is a hexadecimal literal. It has exactly 4 digits after the \u. And it turns out that character 41 is actually an uppercase A anyway. We also have, borrowed from the C programming language, a number of other constant declarations. In this case, \n is for new line. There are more of those, and you can look them up in your own time. The final variable type is the Boolean. Boolean is used in Java to represent logical values of true or false. That's the only 2 values it can have, so it behaves effectively like a 1 bit of storage. The literal values are true, all lowercase, or false, all lowercase. Unlike some other languages, you can't substitute other values where a Boolean is expected. So you can't say, for example, that a non-zero value represents true and a 0 value represents false. We have explicit true and false values, and we have an explicit Boolean type. So, we've taken a look at the declaration of variables, the initialization of variables, the types of variables that Java provides, and the naming convention that we use for the variable names that we are going to declare those variables with. In this module, we're going to take a look at the typing rules that Java applies to its variables, the casting mechanism that we can use to override those rules should we need to, and we'll take a look at the arithmetic and the comparison operators that Java provides. Again, let's start by creating a new project. Again, a Java application, and we will call this one Operators. The first thing we'll do is to declare some variables that we can use. So we'll have a short, an int, and a long. And then, by way of example, we will demonstrate that we can take a simple variable of a short type, and we can assign that into a wider variable. So a short, remember, is 16 bits, and an integer, an int, is 32 bits, and that means that an int is considered wide enough to receive a short, and the assignment is considered compatible. But next, we notice that if we attempt to assign a long value, that's a 64-bit wide value, into a short variable, that doesn't fit. Although we might know that the long value is perhaps small enough to fit into a short variable, in this case it actually isn't, the compiler will refuse to allow that because it can't be sure. So we can't say a short equals a long. And also, if we do arithmetic, here using the addition operator, the plus, if we try to add a long and a short, the result will always be at least as wide as the widest value involved in the operation. So here you'll see possible loss of precision, required short, found long. In other words, it's complaining that this expression has a long type, which is too big to be assigned into this value. So we can't do that either. What we can do, however, is to overrule the compiler and say, I don't care if this loses value, either because we don't care and we're only looking for the low order bits of the result, or because we know that it won't lose value. In this case, we will lose value. If we force this assignment from our long into our short, then what we will get is just the low order bits stored in that short value. So here we're saying, take the long value, cast it, that's what this is called, a cast operator, to being a short. And really that means just chop off the low order 16 bits. So that would be the hexadecimal value BABE, and it would lose the CAFE part of it. It's worth noticing that if we print out the result of this operation, here we'll print out the value of the short and the value of the long. If this assignment worked properly, we would expect the two values to be the same. But in fact, what we will see when we run this, if we build the project and run it, you will see that the output values are different.
CAFEBABE in hexadecimal turns out to be -889275714, and that's the value of A long, but the value of A short is chopped off 16 bits worth from the low order of that. So of course we get a completely different value, and that's the kind of thing that the compiler is worried about and why it doesn't want us to make this assignment directly. Java also provides a full set of arithmetic operators. So as you would expect, we can add, we can subtract, we can multiply, we can divide. So here we take the two decimal values 64 and 64 and add them with the plus operator. Then we can subtract with the minus operator. We can multiply with the asterisk, the times operator, and divide with the division operator, which is a /. Those ones are probably obvious. We also have the remainder or modulus operator. So what we'll see when we run this version is 64 plus 64 should give us 128. Subtract 127 from that, we should end up with 1. Multiply by 100 should give us 100, divide by 10 should give us 10, and mod 4 will say what is the remainder of 10 divided by 4, and that of course will be 2 remainder 2. So if we run that, save the file and run it, we should see 128 from 64 plus 64, the 1, the 100, the 10, and the 2. Java also provides increment and decrement operators. These are actually borrowed from the old C language, still very popular. Here we see that there are two forms of this. We can put ++ immediately after a variable. What that does is to say the value of this immediate expression is the value an integer. But after we've used it, increment it by 1. So what we'll see is that an integer is currently 2, and it will actually still be 2 when it prints out. But if we print it out again immediately afterwards, we'll see that the value is 3. The other version of this, and we can do this with ++ and -, we can put it afterwards, in which case we get the post-increment or post-decrement effect, or we can put it before, in which case we get the pre-increment or pre-decrement effect. So in this case, we'll expect to see this value will print out the same value of an integer, i.e. 2, and then increment it to 3, so this one will print out 3. And then the pre-decrement will reduce the value from 3 to 2 and print it out immediately. So if we run this version of it, we should see that the post-increment prints out the original value, but then results in it increasing. The pre-decrement decrements it by 1 before it makes the value available to the rest of the expression. So remember, we have ++ and -, either of which can be in advance of the expression, like here, or after the expression, as here. Something else that Java does, which again is derived from its heritage with the C programming language, is that assignment itself is an operator and has value. So here the assignment an integer equals 99 actually is an expression with the value 99. So if we print this one, you'll see that assignment value is 99. So not only does this equals operator assign the value from the right side to the left side, it also results in an expression which takes the value that was assigned. While on the subject of things inherited from the C programming language, we also have assignment operators. Here we see an integer plus equals 99. What that does is to take the value of an integer and add 99 to it. There's a couple of things that are interesting about this. If on the left-hand side we have a more complex expression, perhaps something involving arrays, that expression is only evaluated once, instead of being evaluated on the left side and on the right side. This is roughly equivalent to an integer equals an integer plus 99. The other thing that is interesting is that notice here an integer plus equals a long is effectively equivalent to an integer equals an integer plus a long. But remember when we talked before about casts, we said that if we take an operation like this, then the size of the expression will be the size of the largest of those operands.
What that means is that if this was literally an integer equals an integer plus a long, then this would result in a long value that would not be assignable to an integer. But by using the assignment operator like this, the plus equals operation, what that does is to create a situation that automatically casts for us. So it becomes more like an integer equals an integer plus a long cast to an integer. Finally, for this module, Java provides a set of comparison operators. We have the greater than operator, less than, greater than or equal to, less than or equal to, and not equal to. It's important to get the order in greater than equal or less than or equal to correct. You must put the greater than or less than symbol first and the equal sign second. Each of these returns a Boolean type, so 100 greater than 99 will produce the value true, 100 less than 99 will produce the value false. Similarly, for the rest of these, we'll get trues and falses according to the logic of what we have described. So if we run this one, you'll see 100 greater than 99 is true. And notice it really does evaluate to the Boolean value true. Similarly, false, true for greater than or equal, false for less than or equal, false for equal to, and true for not equal to. Recognize that the two equals symbol provides comparison, where the single equals provides an assignment. That's an important difference. So to recap, in this module we've looked at the assignment and the fact that assignment has value. We've looked at assignment and the typing rules and the fact that we cannot assign wider types into narrower types. We've looked at how to cast to overcome that rule if we need to. We've looked at the basic operators for arithmetic: add, subtract, multiply, divide, and modulus. We've looked at the increment and decrement operators, and we have looked at the assignment operators, plus equals, and we have looked at the comparison operators. In this module, we're going to take a look at the conditional statements using if and switch that Java provides. Create a project. We'll call this one conditions. And then the first thing we're going to do is to put a couple of variable declarations and a simple conditional statement in there. So here you'll see we have an int value a of 99 and another int of b with the value of 100. And we have this simple statement, if a less than b, and then immediately following it we have the curly braces. And the curly braces ensure that what follows appears to the compiler as a single statement. So everything inside the curly braces will happen only if a is less than b. Well, of course a is less than b. So if we save and run this, we see that it says 99 is less than 100, so it's printing out the statement that was in here. If we'd momentarily change the value of a to 199, we should see, as we expect, that it no longer outputs anything. Of course, that's not terribly helpful, because now we don't know whether it actually just did nothing because there was a problem with what we wrote, or whether in fact it was correct that it did not print anything. So the other thing we can do with an if statement is add an else clause. So in this case, if we say else and then a is greater than b, now it should print one or the other no matter what. So if we run this one, remember a is still at 199, so it prints the contents of the else clause, this one here. So that's if and else. You don't have to have an else, but it's available to you. And similarly, you can nest these if you want to, so you could say else if and things of that sort. Another form of condition that Java provides is the switch statement. Switch statements look like this. We have the word switch and then a simple expression. In this case, we have the value a, and then a series of case statements. Each of the cases will be compared with the value in A at the time when this runs. So at the moment, of course, the value of A is 199. So the case for 98 will not match, the case for 99 will not match, nor will the case for 100. The result will be that because we have this default statement, when we run this, the code will jump straight down. As soon as it does the switch, it will recognize that A does not match any of the specifically expressed cases, so it will jump to the default and print out A as something else. So if we run that, A is something else. If we change A back to 99 and run that version, and we see that it says A is 98 or 99. Well, that raises an interesting question. Here we have two case statements just run together. You'll also notice that each of these cases has a break at the end of it, except for the case of 98. The behavior we're seeing here is actually inherited from the C programming language. And what it says is that when you have a switch statement and it jumps to a matching case, execution carries on from that case until or unless it reaches a break statement. So the execution for case of 98 is effectively that it jumps into this empty region here and then just carries on past the label, in effect, of case 99, and therefore prints out A is 98 or 99. Then when it hits the break, it jumps to the end of that case statement. Of course, what that sometimes means is if you intended, let's duplicate this in here, if you intended to print out one value, so here we'll say A is 98, and then here we'll say A is 99, and you omit the break, so notice there's no break after this one, let's set A to the value of 98 and then run this. Notice it jumps into here, it says A is 98, but then it falls through, that's the term that's usually used, because there's no break statement right after this, it then carries on as though nothing had happened, prints A as 99, and then hits the break statement, at which point it drops out. In fact, just to emphasize this, notice that if we take that break out, now we see it prints 98, falls through to 99, falls through and prints 100 before finally hitting a break. So in most cases, it's important to ensure that you put that break statement in your case clause. So here we're back to A is 98 or 99, and the logic makes sense again. So this lesson introduced the if statement with its accompanying else and the switch. In this module, we're going to take a look at the loops that the Java programming language offers. Java offers three loops. We have a while loop, a do-while loop, and a for loop that is inherited from its C origins again. Let's create a project. We'll call this project loops. And the first thing we'll do is to insert in here some simple code for a basic while loop. Notice we start with a declared variable for int a. We set its value to 0. And then we say while a is less than 10. So the control of the while loop is a Boolean expression. And for as long as a remains less than 10, we will expect to keep going around the body of this loop. Then inside of the loop, we simply print out the value of a, and we increment the value of a. When we're done, we print out finished the loop. Save that one and run the code. You'll notice down here that a prints out for 0 all the way through 9, because at the point at which a increments to 10, a is no longer less than 10 and it will drop out of the loop. That's the while loop in its most simple form. One important feature of the while loop is that it might execute no times at all. So for example, if we repeat the same code, while a less than 10, and then print that out, it's probably no big surprise that because a is already 10 from here, this code will never execute the next time. So if we run this one, we'll see again, it counts to 10, says finish the loop, and then immediately says finish the second while loop, because the condition never matches. The next type of loop that Java offers is the do-while loop. In the case of the do-while loop, here's the code for this one. We start out with the keyword do, and then we immediately enter our block. And inside the block, we do the code that we want to have happen repeatedly. So we can print out A is and the value of A. We can increment A. And then our while condition goes at the end. Now in this case, if we say while A less than 10, based on this preceding loop, one might wonder whether this was ever going to execute at all. You're probably familiar with the do-while style of loop, and the major difference with this loop is that it always executes at least once. It comes in to the body of the loop, runs the body, and then tests the condition at the end of the loop. So even though A is already not less than 10, this will execute just the once before it discovers that. So if we run that one, we see the same code we had before, runs through to 9, says finish the loop, finish the second while loop, then it prints A as 10, and then says finish the do-while loop. So a do-while shouldn't be too difficult to use, just remember that it will always execute once. The third type of loop in Java is inherited again from the C programming language, and this one is the for loop. So here we have code that comes in and this says for, and then there are 3 sections to the body of the for loop itself. The sections are separated with semicolons, so there and there. There's the second semicolon, there's the first. The first part of the for loop is called the initialization section. It's quite common to declare variables in here, but they don't have to be declarations. They can simply be an initialization, or as you'll see in a moment, you can actually leave them out entirely. So this one declares a variable x and initializes its value to 0. The second piece inside the for loop's control structure is a condition. This behaves as a while condition. So what this one says is, for as long as x is less than 10, then we will execute the body of the loop. And the third piece is this piece here. This is executed at the end of each body of the loop. So what will happen is every time that the body of the loop has completed and we get to this point here with the closing curly brace, it will execute this statement and then perform the test specified here, and it will come back into the body of the loop if this conditional piece here is true. So in this case we can reasonably expect that x is first printed out as 0, and then it will print through incrementing until it reaches 9, and then it will drop out of the for loop. So if we run that one, you can see down here, after the do while loop, x is 0 through x is 9, finished the for loop. Another piece of the for loop that is worth noticing is that in this declaration, if we create a variable declaration here, the scope of that variable is limited to within the curly braces and the body of this control structure. So here we have a statement, print out x, but you'll notice if we uncomment this, that this is actually an error because the variable x is out of scope at this point. It exists inside this block here and then inside the curly braces. By the time we reach this point, it has ceased to exist. So we can't do that one. Another feature of Java's for loop, again inherited from C, is that we do not actually have to provide all 3 of the elements of the control structure. So here you'll notice the first element, the initialization piece, and the last element are both empty. All that means is there is no initialization section, and nothing special happens at the bottom of this. This actually becomes identical to a while loop that says while a less than 20. While a less than 20. You'll sometimes see people leave sections of this out, so it's important to realize that those can be left out. You don't have to, they can be left out independently. So if we run this version, you'll see now it's going to be picking up from where it previously left off with A. So A was already 10 as a result of the do while loop, and now it picks up at 11 and goes through to 19, exactly as if it had been a while loop. The logical conclusion of leaving these pieces out is that in fact we can leave all three pieces out. If you leave the middle conditional piece out, then this becomes effectively an unbounded infinite loop. So you'll often see this structure, for parenthesis, semicolon, semicolon, close parenthesis. You can read that as forever, because that's effectively what it will do. It doesn't set up any precondition, it doesn't do anything each time around the loop in this control structure, and the condition is considered always to be true. Well, that creates an infinite loop, which is why I suggest you can read it as forever. That allows us to introduce another feature of loops in Java, which is that we have a break statement that we can apply to a loop. If we execute break while inside a loop, what will happen is that we will jump out of that loop completely. So here we start out by saying go around this loop forever, but then we cheat and internally we say if A is greater than 25, then skip out of it. Otherwise it would be a rather long-winded example because it would never finish. So this time we know that A was previously left as 20 from the preceding loop, so we'll count another 5 times, and when A is greater than 25, after we've printed out 25, then we will jump out of the loop and say finish the third for loop. So we run that one, and here you'll see that we finish the second loop. A picks up at 20, prints through to 25 inclusive because we test after we've printed it out, but then we do in fact jump out and we execute this print of finished the third for loop at the end of it. So in this lesson we looked at Java's 3 loops. We have the while loop, the do while loop, which is very similar to the while loop but guarantees to execute its body at least once, and the for loop, which can simulate the do while loop but also allows us an initialization section and a place to put the behavior that occurs immediately at the end of each loop, setting it up ready for the next time round. In this module, we're going to take a look at arrays in Java. We'll have a look at the syntax for declaring a variable that refers to an array, and for creating the literal initialization of an array. We'll have a look at how we access elements of an array and the valid range of subscripts that we can use within that. We'll also note that arrays are of fixed size, and we'll learn to determine the length of an array. Sometimes arrays being of fixed size will be a problem, so we'll find out how we can deal with that and make an array that is bigger than the one we started with. Finally, we'll take a look at Java's version of multidimensional arrays. So let's get started by creating a project. We'll call this project Arrays. And the first thing we'll do is to create some very basic code which declares a variable called values, which is described as being an array of int. Notice we take the basic type int and we put the square brackets immediately after it. These two combine to form a single type declaration that says values is an array of int. Then we initialize this by using this literal format for declaring an array where we take curly braces and then we put a comma-separated list of values within the curly braces. Finally, we close the curly braces and put a semicolon on the end of the line to complete it. So now values describes an array of integers containing the values 1, 1, 2, 3, 5, 8, 13, 21, and 34. The next thing we need to be able to do is to actually use one of the elements of the array. The way we do that is simply to take the array's name, values in this case, put square brackets after it, and to put an expression that describes a number, which will be the element number within that array. So values subscript 4, these subscripts always start at 0. So this would be the subscript 0, this would be subscript 1, this would be subscript 2, this would be subscript 3, and this will be the element at subscript 4. In other words, values square brackets 4 is really the 5th element of an array. So we would expect this to print out the value 5. So let's run this program. And we see indeed the 5th element of values is 5.
If we were to change this to the value 5 and make this 6th, then we should see that we pick up the value 8. And indeed we do. The next thing we need to know is that if we try to access an array element that does not exist, then we will get a problem at runtime that we will need to fix. So in this case we have 9 elements in there, and if we were to try to access element with subscript 10, which would really be the 11th element, this will actually cause the program to fail by doing what's called throwing an exception. And you'll see this exception in thread, array index out of bounds exception, and the number 10 is the subscript that was given to it that it didn't like. If you click on this little piece, by the way, if I move the cursor away from there, notice how the cursor is currently here. I click on here and that actually moves to the line where the error occurred. So NetBeans has this quite useful feature for determining where the problem actually arose. So let's put this back to something that works. We'll go with values 4 and we'll make this the 5th element. Given that we are restricted to accessing elements that actually exist, and that the elements start at subscript 0, we need to know sometimes how many elements there are in an array. So it turns out that if we put this expression .length on the end of the name of an array, so here we have values .length, the array itself knows how many elements it has, and we can effectively ask it. So in this case, if we run this, we'll see that there are 9 elements in values. Remember that the elements will be numbered 0 through length minus 1. So the valid subscripts are from 0 to 1 less than the value of length, so in this case up to 8. If we want to print out all the elements of an array, we can use a loop to do that. So here, notice we use a for loop. We start off with an index value of 0. And then while the index is less than the length of the array, we will print out that particular value with that subscript. And then each time round the loop, we will increment that subscript value. So here we will expect to print out each of the elements of the array in turn. And as you can see, it prints out values 0 is 1, values 1 is 1, runs its way through the elements. Subscript 8, which is the 9th element, prints out 34. In addition to being restricted to accessing the elements of the array that already exist, Java's arrays are also of fixed size. So we can't add new elements to an array. So for example, if I were to attempt to set values 9 to 55, that's not going to work. We'll actually get the same error that we would get if we tried to read the value of values 9. Interestingly, the exception is not always printed out in sequential order with the problem that caused it. The reason for that is simply because the error stream is a separate channel from the output stream, and in consequence these things arrive at the console sometimes in the strange order. But you'll see here it's complaining that we cannot access the element number 9, subscript 9, of an array that only has 9 elements, which are therefore numbered 0 to 8. So that doesn't work. So what happens if we have an array and we need to add more elements to it than it already has? The way we have to handle this is actually to create a new array, and we do that like this. We declare a new variable, and then what we do is we say equals new int square brackets, and inside the square brackets we can specify the number of elements we would like this array to have. Now we actually can do this at any time. There's nothing special or unique or reserved about this, special to creating a larger size of array. But what this does is to create a new array, and interestingly all the values in this, which will obviously be the subscripts 0 through 19, because this is a numeric array, all the values will be set to 0. Then what we can do is we can copy the existing array into the new array. And for this we have a special mechanism provided by Java, system.arrayCopy. You can probably guess we could do this by hand with a loop.
but that would be potentially less efficient than this. So the way system.arrayCopy works is we specify the array we are copying values from and possibly an offset within that array. Well, we want to start at the beginning. Then we specify the array we're copying values to, and again an offset within that array, and then the number of elements that we want to copy. In this case, all the elements in the values array. Having done this, we'll contain all these elements from the original values array, but also will contain additional elements all at the value 0 up to the subscript 19. Now that we have a longer array, we can add the additional values to it. So now we can set the value of more values 9 equals 55, and then we can print out more values 10 if we want to, because that value exists even though we haven't set it to a special number, therefore it will have the value of 0. So here you can see more values 10 is 0, and this assignment of more values 9 did not cause a problem like it did before. Many programming languages provide multi-dimensional arrays. In some ways you could look on Java as the same in that we have the ability to use something that looks like multi-dimensional arrays. Technically, it actually isn't considered as providing multi-dimensional arrays. What we do get, though, are arrays of arrays. And they're very similar. They'll do everything that multi-dimensional arrays will do, but they're also subtly different. So here, remember we said that when we put the square bracket after the int, that meant that the variable we were about to name was an array of int. Well, here we've got a square bracket after the square bracket that's after int. And the way to read that is that this is an array of whatever comes to the left of it, which in turn is array of int. In other words, it amounts to a two-dimensional array. But what we discover is then when we define the array, we provide the curly braces that introduce the definition of the array, but then the elements of the array are not numbers. The elements of the array are actually arrays themselves, and these are arrays of ints. But you'll notice that here this array has 3 elements, this array has 2 elements, and this array has 4 elements. Because this is not a multi-dimensional array, but is actually an array of arrays, that's perfectly okay. You still access the elements within these arrays of arrays the same way you would have done for simple arrays. So in this case, ragged matrix 0, 2 will pick up, first of all, ragged matrix is the whole thing. Ragged matrix 0 refers to this whole array. Ragged matrix 0, 2 is therefore element 0, element 1, element 2, and should print out the 3 that we have here. So if we run this one, we should see ragged matrix 0, 2 is 3. So in this module, we've looked at the declaration of arrays, the initialization of arrays, accessing the elements of arrays, the length of arrays, how to iterate over arrays, what happens when you don't have enough space in an array, and how we can handle multi-dimensional arrays in Java. In this module, we're going to look at the basics of declaring and invoking methods in Java. Methods can be used for a variety of reasons, but one of the most common is that you have a block of code which you're going to use in several different places. So rather than write it out all over again, you can group it together, create one method, and then call that method from those multiple places. In many other languages, methods are actually referred to as either functions or procedures. Let's start by creating a new project. We'll call this one methods. And the first thing we'll do is put some code in here which will compute the average of a small array of numbers. So here you see we declare this array, float array, called FA1, and it contains 4 floating point numbers, 1.2, 3.2, 5.9, and 9.6. Then we declare another variable called sum, again its floating point number. We initialize its value to 0, and then we run through the array using this for loop that counts from index of 0 to the index limited by the length of that array. And for each element, we add that to the sum. Then the average is computed by taking that total sum and dividing it by the number of elements in the array, fa1.length. And we print that out. So if we look at these numbers in the array, the average looks like it's probably somewhere around 5. We've got almost 10 there, about 6 there, 3 and 1. So they're spread fairly evenly. And if we run this program, we see that the output average number is about 4.9. So it looks kind of believable. So suppose that we want to compute the average of another set of numbers. We could simply write out the same code all over again. So here is a new array of floating point numbers. We've called this one fa2. Notice this has 6 numbers within it. We reinitialize our sum variable to 0. And then we run through the array fa2 based on 0 to fa2 length for the indexes. And then we add each of those elements to the sum again. And then we compute the average using sum divided by that amount of numbers. So if we run this program, we should see we get a slightly different value. But again, these numbers are spread fairly evenly between 0 and 10. So it's not a big surprise that the average is about 5. Well, the issue here is that we have almost exactly the same code repeated there, where we start by initializing the sum to 0, then we add to the sum each of the elements of an array, and then we compute the average by taking the sum divided by the number of elements. So this code has been duplicated. Clearly, duplication has 2 problems. One is that we have to write it out twice, which is rather a nuisance. And the other problem with that is that if we discovered there were a bug in this piece of code, we would have to remember to fix it twice instead of fixing it once. So what we would like to be able to do is to take this chunk of code out and reuse the same code in both these places. And to do that, what we're going to do is to create a method. So the method is going to be created separately. You'll notice at the moment we've actually been ignoring the fact that we are inside this method called main. We're actually going to create this method outside of that, but still inside of the class for methods. So there we have the method declaration. Let's take a look at this for a moment. The first piece is we're going to take more or less on trust for the time being. In other modules we'll discuss what these mean, and we may find some variations on them. We're going to label this as public and static. Then the important pieces that we want to discuss right now, each method returns a computed value to whatever piece of code called it. And the type of the returned value is declared here. So in this case, we're saying that when we compute an average, what we will get is a floating point number. So we declare the return type float here. Then the method's name is average, so that's what we're going to call it as when we need to invoke this behavior. Then we can specify arguments that this method requires to do its job. So this is information that's passed into the method from the outside so that it can do its work. Then inside the method, we do pretty much what we did before. We declare our sum variable of type float and initialize it to 0. Then we go through the whole contents of the array. Notice this time we refer to fa.length. So that's saying whatever array I was given, iterate over each of the elements of that. And in fact, we pick up fa idx each time round and add it to sum. Finally, we divide the total sum by the length. And this statement here, return, says this expression, compute it, and pass it back to the caller. The argument to this type, must match the type that we said we were going to return up here. So that declares a method called average that takes an array of floating point numbers as an argument and returns a floating point number as the computed result. Let's see what it would take to actually invoke this code. All we have to do to invoke this is to refer to it by its name. So here the expression average fa1 refers to it by name and provides it with an argument of the suitable type. This call, method call as we would call it, is actually considered to be an expression of whatever the return type specified here is.
So we can put this in, and the call to average using fa1 as the argument will be representing a floating point number, and that floating point number will be printed out. So the neat thing about this is we can call this twice. Notice the first time we say the average of the first set of numbers is, and we continue the line here so it doesn't get overly long with plus average of fa1. We pass it the values in the floating point array called fa1. It computes the average and it prints out average of the first set of numbers is 4.9 something. Then we do it again. Average of the second set of numbers is, and here we call the average method using fa2. So it's the same behavior but with a different set of numbers as the argument. So if we run this, we'll see that we get the same behavior and the same output that we got before from the pieces we had previously, these elements up here. But then our new ones, average of first set of numbers and average of second set of numbers, here we get the exact same values because the implementation of the method called average is essentially identical to the code that we had previously just sitting in line. So that's a simple method declaration. Well, sometimes we might need more than one method. It's perfectly reasonable to have a variety of pieces of behavior that we want to create methods for so that we can reuse them. So let's create a variation on this theme. Again, it needs to be inside the class, but outside of our main method. So here we've declared another method. We're calling it partial average. And you'll notice that this takes a floating point array, but then it takes two integers, first and last. It still returns a floating point number. It creates a variable called sum and initializes it to 0. Notice that we can keep using the same variable name because the sum in this method is a different variable from the sum in that method. This is only visible inside the enclosing curly braces. So from this curly brace here to this curly brace here, this variable sum has meaning. In fact, you can see that NetBeans has highlighted it. When I put the cursor on there, that one, and that one are highlighted as all being the same variable. These ones aren't. Anyway, what we do with this variation is we compute the sum just between the first and the last indexes. So for idx is first, idx less than or equal to last, add up the sum, and then divide by 1 plus the difference between those. The point being that if the first and the last were the same number, we actually would have computed the sum of one number, so we still need to divide by 1 plus that difference. So now we can invoke this partial average method. Let's have a look at the code to do that. Probably not a surprise. We have our print statement. It prints out the message, and then it concatenates with that the result of calling partial average, giving it the array of floating point numbers fa2 and a beginning and ending index. So if we run that, we'll see that it computes a believable average. 5.1 is probably somewhere about right. Remember, it's computing the indexes. That's index 0, that's 1, that's 2, that's 3, that's 4. So it's adding up those four numbers and dividing them by 4. Well, one of the interesting things about object-oriented languages is that we can actually reuse method names if we want to, under certain circumstances. So it turns out that really this isn't a partial average. What it is the average, but the average of only a partial set of the numbers. And we can actually call this method average. Notice I've changed the name here to average, here to average. They're both the same name. But the reason the compiler is okay with this is that it can tell by the argument list that they are different functionality. So if I change this also to average, you'll see it's happy still because it knows that if I ask for this average, it needs the piece of code, the method, that takes a floating point array and then two integers. If I ask for this average that just takes a single floating point array, it knows that it must use this average method based on that. This is called method overloading. And really what it means is if you need to describe what is essentially the same operation
but with different input data, then you can actually use the same name. Don't do this unnecessarily because it could be confusing, but it's important to recognize that this is allowed in many object-oriented languages, and Java is one of those. So, in this module, we looked at the basic reason for declaring a method, the process by which we declare a method, how we give it a name, a return type, and its argument list, and how we invoke a method, along with the mechanism by which we can reuse the same name, known as method overloading.
Welcome back. Now that you know how to use the basic procedural type aspects of Java, it's time to start looking at how we can handle more complex data, things that you might find in the real world. As before, we're going to start from principles that are more likely to be familiar to you. We're going to start by talking about how Java would create structures. Structures, of course, are how you handle complicated things like customers or objects on a supermarket shelf in a regular procedural programming language. It turns out that structures are actually the basis of objects, so it makes quite a useful stepping stone from a learning perspective. We'll show you how to make structures, and then we'll show you how to make them a little bit more special and how to turn them into objects. There are really two things that separate an object from a simple structure. The first is that with structures, one tends to have pieces of program code lying around the system that can operate on and manipulate those structures. With an object, it's a little bit more controlled than that. With an object, the behavior, the program code, that can manipulate the object, or the data structure if you prefer, is actually part of the object itself. And we're going to show you how you can create code that belongs to what otherwise appears to be a data structure. The second piece of what makes an object distinct from a data structure is that in the case of a regular data structure, any piece of program code that wants to can change the contents of that structure. In the case of an object, however, only code that belongs to that object can do that. Might seem like a strange thing, but it actually creates a very powerful control mechanism so that if something goes wrong, you know where to look. And if you know where to look, you're usually only looking through a few hundred lines of code instead of maybe a million lines of code in a really large program. This makes it much easier to create reliable, robust, and correct programs in situations where you have lots of programmers all cooperating on the same thing, because somebody else isn't going to make a mistake that corrupts your data structure. This mechanism by which an object can protect itself from misuse on the outside turns out to be extremely valuable when it comes to writing libraries. When you have a Java library, you'll usually find that it's pretty easy to use. One of the main reasons it's pretty easy to use is that it looks after itself. The objects that you create when you use that library will protect themselves from being misused. And in general, what's going to happen is that you'll find that if it looks like you think you should use this object in a certain way, the chances are you're right. If it turns out that that is not the way you should use it, the object's going to tell you instead of merely failing. And that way you can correct your program before it ever goes to production, and you will find that your productivity with good object-oriented libraries will usually be much higher than you are accustomed to with procedural type environments. Before this part is finished, we'll also take a few minutes to look at a couple of conceptual things, pieces of terminology. You'll often hear people talk about classes and objects. What's the difference? Well, classes in general are the templates that say how something should be made, and objects are the things that are made. We'll take a little time out in one of the lessons and have a look at that so that you'll feel thoroughly comfortable knowing what that means. There's another piece of terminology that is less specifically object-oriented and relates more directly to the way Java is put together. This is the idea of a package. A package is really just a way of clustering together related classes so that when you're working on one particular aspect of the program, you can find everything that you want all in one place. Of course, it's not always quite as simple as that, but that's the general idea.
Because Java is used to make extremely large programs with potentially millions of lines of code, if you had to look through everything all in one place, it would be very difficult to find what you were looking for. So the packaging mechanism allows you to group together related things, and then you know that if you're interested in a certain aspect of the system, there's one particular group of code that you'll go and look at. This also makes it easier to find library code. You'll find, for example, that there is a package related to doing I/O operations, such as reading and writing files. And there are packages for a great many other things. There's actually quite a lot of them in Java. But we will have shown you the documentation for Java, so you'll know where to find them too by the end of this part.
In this lesson, we're going to learn to create and use structured data types in Java. Many languages provide the ability to create user-defined types. These might be called structures, or structs, or records, or other names. In an object-oriented language such as Java, the use of simple structures is discouraged. There's a better idea called classes and objects that we will learn. But understanding structures is a foundation of understanding objects, and the syntax of structured types uses the syntax of classes. So we're actually just taking a first important step on a journey. Think about a program that will look at packages on a supermarket shelf. Each type of product, each item if you like, has a name, a price, and a particular quantity of product in the package. Let's create a simple structured type to describe this. We'll start by creating a project. So I'm going to come over here and click on the New Project button. It's going to be a Java application. And I'm going to call this structures1. The main program file, structures1.java, is actually not where we're going to define this structured data type. We'll write a program in here that will use our structured data type, but we're going to define it in a separate source file. So to do that, we're going to come across to the Project Explorer window over here, and you'll see there's our Structures1 project. It has source packages, the Structures1 package as it's called. You can see the little brown paper parcel that describes a package. And then structures1.java there is this source file. What we want to do is to right-click on the Structures1 package and say New Java Class. We're going to call this Java class item, and then we'll say finish. What NetBeans has done for us is to create this skeleton of an empty structure. You'll notice it says public class item. Remember we mentioned that class is an idea that encapsulates the idea of a structured data type but with extras, and that's why this is actually called a class even though we're only looking at it as a structured data type. The name given to our type is item, and the fact that it's public is something that we're not going to discuss in this lesson, but means that it's essentially accessible from anywhere. What we want to do is to define the contents of an item as containing the three elements: a name, a price, and a quantity. We're going to use Java's data type string, which represents sequences of characters, to represent the name. Then we'll use an int type for the price and also an int type for the quantity. Programmers generally will use integer types for money where possible, so this is obviously in cents rather than in dollars. And the quantity may be whatever units we think are appropriate, perhaps ounces or sheets of paper or whatever. That is actually sufficient to define a basic structured data type. Every time we create an item, it will have these three parts: name, price, and quantity. So let's look at how we'd use it. To do that, we're going to go across and click on here, select the structures1 file, which is going to be our main program. I'm going to delete the comment. And then the first thing that we have to do to use one of these structured data types is to declare a variable of that type. Like any variable declaration in Java, we start with the name of the type and then we specify the name of the variable. So in this case we can say item and item. Now interestingly, Java does not create the storage for the item when we say this. What it's actually done is to create a single variable that will refer to or point at
an actual item. So the next thing we have to do is actually create the storage and make an item point at it. The way we do that is using a special keyword in Java, new. So here, by saying item an item, we've created a variable that will point at an item. And then by saying new item, we've actually created the storage. So there we have the declaration and creation, or as it's sometimes called, instantiation of an actual item. Now that we have the storage in memory, we can start to use it. Because we have a name, a price, and a quantity, we'll actually want to set those values to contain something meaningful. And the way we refer to the elements within one of these structured data types is by using this dot operator. So an item points at the whole item. An item dot name says go and find the name piece of an item. So we can use this an item dot name equals Frosty Crunches to specify that the name of this particular item will be Frosty Crunches. And then we can set its price to 250 cents, $2.50, and its quantity to 28, perhaps ounces. So now we're using the storage to describe one item. Well, to be useful, of course, we probably don't just want to describe a single item, we probably want to describe more than one item. We can do that essentially just by repeating what we've already done. So here we have another variable declaration, item, another item, so that's another pointer that will point to another item. And then we create the storage in memory for it, new item, and then we set the name, the price, and the quantity of another item to generic cereal at $5, but the package is twice as big at 56 ounces. Of course, we don't just want to be able to store things in this, we want to be able to get at those values as well. We can actually use the same syntax with the dots to look at the values that are stored there as well as to write things into them. So here we can say, let's print out an item's name, concatenate comes in, and then concatenate an item's quantity, unit packages, and costs, and then say what the price of that item actually is. And of course, since we have two of them, we can do that with both of them. So here we print out the details of another item. Let's save that file and run it. And you'll see Frosty Crunches comes in 28 unit packages, we know they're ounces, and costs $250 per package, and we know those are cents. Generic cereal is in 56 unit packages and costs $500 per package. Well, of course, if we have multiple items, we probably don't want to have to print them all out individually, so what we could do is actually to create a method that will do the printout for any given item. Let's see what that would look like. Methods, of course, need to be placed outside of other methods, so we'll come up to this top piece here, inside the class, but outside the main method. And then we will declare a new method, and this one is going to be called displayAnItem. It takes as its argument an item, which will be the item to be displayed. And then you'll see that the body of it is identical to what we just had. It just prints out an item's name, some text, an item's quantity, some more text, and then an item's price. In this case, the return type of this method is described as void. That's to say, it doesn't compute anything that it has to give back to the caller. And void is the way we would specify that. So now we want to comment out these lines because we're going to replace this behavior by calling that method. So if we select those lines by clicking and dragging, come up to source and then find toggle comment, you'll see that it puts the double forward slashes in front of each of those lines, and these lines have now been commented out. We can prove that if we save the file and run it. You'll see that we get no output, so we have successfully taken that away. So now what we need to do is instead to call that method we just created twice. And so we'll say displayAnItem and give it an item, and then displayAnItem, same method, another item. And if we run that, you'll see that we back to the same original output. So there we have it, our first use of a structured data type in Java. The item describes how an item should look with the name, the price, and the quantity, and then we can create occurrences of that in memory by saying new item, use a variable of type item to refer to that, and then we can refer to the name, the price, and the quantity elements within it as we need to. In this lesson, we're going to look at how the object-oriented approach that Java uses allows us to add behavior to our classes. For comparison, in procedural languages, we typically define our structured types and then create utility methods to operate on them. But this leaves a separation between the way that a structured type is represented in storage and the way that it is manipulated. Object-oriented languages move the code that operates on a data structure into the class that defines that structure. In this way, the association between the two is clearer. We know that the behavior is intended to work on that structure. Also, we can see, when we edit one part of it, what changes might be needed in the other part, so we're less likely to introduce bugs when we make changes to our code. To investigate this, let's look at a data structure that defines a day on a calendar. We'll start by creating a new project. Let's call the project Date1. Here is the Date1 class that contains the main method that we're going to use to create the program that's going to do things with our date. But the first thing we want to do is to create the date class itself that's going to represent this data structure. So we'll right-click on the Date1 package and go New Java Class, and we'll give it the name Date. This gives us the skeleton empty class definition for date, and what we need to do is to put into that the definition of the variable elements that will define the structure for a date. So it seems reasonable to think that we will have three pieces to it: a day, a month, and a year, and that we might use an integer to describe each of those. So there is our basic date data structure. We'll start calling them class now. And then to use it, we'll come into our program code that is going to be this Date1. And to use one of these things, remember the first thing we will need is a variable. So we'll call this meeting date, and we'll declare it as being of type date. Then we use that variable to refer to an actual date that we create in memory. So new date will create the physical allocation of memory that will have the elements month, day, and year within it. Then what we'll do, we will initialize the month to 2, the day to 29, and the year to 2012. February 2012 is a leap year, so the 29th is perfectly sound. And then we'll print out the meeting will be on, and then we'll print out the pieces, month, day, and year, of that data structure representing our meeting date. So we'll save the file, and then we'll run it. The meeting will be on 2/29/2012. So far, so good. We know when our meeting will be. The next thing that we notice is that if we create a lot of these dates, having to initialize them by carefully stating that the meeting date .month is this, and .day is that, and the year piece is that, gets a little tedious. That's a lot of typing to do, replicating this date variable .month and so forth. So it turns out that one of the pieces of behavior that we can add to a class is a mechanism for initializing the objects that are created in memory, the instances of that data structure, if you will. The way we do this looks a little bit like a method. It actually isn't a method, it's called a constructor. What we do is we start off with the keyword public, and then we go directly to the name of the class itself. So our class is called date, and so we put public date. If this were a method, remember, there would be a return type declared in here, int or void or something of that sort. But the absence of that return type, plus the use of the exact class name, and this must be correct with regards to capitalization as well, tells the system that this is a thing called a constructor, a means of initializing objects of this type when they are created. And then in the parentheses, we specify the arguments. So to initialize one of these, we'll need to provide a month, a day, and a year. So we'll refer to those as the ints m, d, and y. Then what we need to do is to take this particular object that has been created in memory and set the day, month, and year elements of it based on these month, day, and year, or m, d, and y variables that are provided in the argument list. So this .day refers to the particular occurrence of this day variable inside this object as it's being created. Now it actually turns out that it's possible to leave out this dot, but we're going to use that fairly consistently because it makes it a little clearer exactly what's happening. So now what we've done is to say that in order to create one of these date objects, we must provide it with a month, a day, and a year in this argument list in the constructor. And that means that this piece is actually going to complain because this does not provide those elements. So what we now need to do is to modify this so that we specify the month, the day, and the year, and that will be sufficient to initialize what's going on in this particular meeting date. So the next thing I can do is I can select these three lines, go to Source, Toggle Comment, and I can actually comment those out. If I save this code and run it, you'll see that it still actually works exactly as we specified. Just to prove that it isn't, that these lines didn't really disappear, let's change this to March, save it and run it, and you'll see that it really did pick that value up. I'm going to put this back to February. Well, the next problem is, suppose that somebody decides that they're going to change the date of this meeting. They decide that the 29th of February they're busy and they need the meeting to be tomorrow. So what they attempt to do is to increment the day field. Now, you can probably see where this is going, and it's probably reasonable to think that if you were manipulating somebody's date structure, you would be careful not to make this mistake. But many structures are more complex than that, and you wouldn't necessarily know what the internal rules for its integrity are. So let's just demonstrate that, of course, when we run this now, what happens is that we end up with a meeting scheduled for the 30th of February, which of course doesn't exist. Well, it turns out that using this mechanism of embedding behavior into our objects, into our classes, we can actually build a security mechanism that will help us to avoid this kind of error. So let's go and look at our date class again. What we really need is to be able to ask the date to modify itself by going to the next day. So what we're going to do about this is to add behavior to the date class that allows the date class to deal with all the complexities of a leap year. So let's take a look at this. What we've added is a method called nextDay. The nextDay method looks at how many days there are in this particular month based on the month and year that this object represents. Notice again we have lots of references to this.month and this.year. Those refer to the month and the year, and this.day would refer to the day of the particular object that is currently being discussed. So the first thing that we do is to determine how many days there are in the month of the year that this particular date currently represents. So we have this method that we've just added called days_in_month, and that one is defined here. Days_in_month takes a month and a year and then uses a switch statement and our little old rhyme about 30 days hath September, April, June, and November to work out how many days there should be in that month. So if the month is one of those 4 months that has 30 days, we set this integer value RV, which stands for return value, to 30. If it's not one of those and it's not February, then we set it to 31. But in the case where we're dealing with February, then we have to determine if this is a leap year. If this particular year is a leap year, then the number of days in the month will be 29, otherwise it will be 28. The computation for leap year looks to see if year mod 4 is 0, that means that if the year is divisible by 4, and the year mod 100 is not 0, that is to say the year is not divisible by 100, or Alternatively, the year is divisible by 400. Most of us think of leap years as being the ones divisible by 4, but strictly there are these little extra rules. So between these pieces of behavior, we can now determine how many days there should be in the particular month. Then what we do is to move the day counter to the next numerical day, but then compare it with the number of days that there should be in this particular month. So if this .day has become greater than the day count we computed here, then we set the day back to 1 and increment the month. The possibility is that we might just have wrapped around December 31st, so we have to look out for the month being 12, in which case then the month, if we had done this increment, needs to be set back to January and we increment the year instead. So this behavior for next day has now become part of the definition of the structure of a date. Save that file and let's see how we use it. So what we now have is a date that is capable of recognizing how to create a reference to tomorrow. Here's some code to take advantage of that. What we're going to do is we're going to create another date object and we'll set it again to the 29th of February 2012, and we'll call this one, we'll use a variable for this one, better meeting date. Again, it's a date type. Notice the way we refer to next day with this same dot notation that we used for the elements that were data elements. So in the same way that we said, I want to refer to the month that belongs to a date called meeting date, now we're saying I want the next day behavior that belongs to a particular date, the one called better meeting date. And this, by the way, is how this keyword in the date class itself knows which particular date object we're referring to. The variable here, better meeting date, will become the value this inside here. So that's to say that the day that we're incrementing here is the one that belongs to this, which is this, the better meeting date variable here. So what now happens is we tell the better meeting date, move to the next day, and instead of simply incrementing the day counter to 30 and producing a bad date, it should increment to 30, recognize, because of our tests here, that that's no longer valid, and do the necessary increments to wrap around and start the beginning of March. Let's save this file and check what happens when we run it. So we still have our existing behavior back here where the regular meeting is now apparently scheduled for a date that doesn't exist, February 30th, but the better meeting will be on 3/1. So in this lesson, we've looked at how we can add behavior to our structures, our classes as we're now calling them, and that behavior can therefore provide the facilities for manipulating our data structures in a closely coupled way that allows clear cohesion between the state pieces, that is to say the variables and the intended way that we expect to use those variables, and the actual behavior of the utility methods that we provide for them. And this is the foundation of objects. In this lesson, we're going to look at implementing encapsulation in Java. Encapsulation is the essential idea that really separates objects and classes from structures. In a data structure that includes behavior, you know that the behavior is closely associated with the data, so it's clear what methods should be used on the objects. And we'll know when performing maintenance that we need to ensure that the methods and the data structures need to stay in sync with one another. Encapsulation allows us to prevent direct access to the data elements, instead forcing users of the object to interact only with methods. This might seem like a bad thing. After all, does this not simply prevent you from doing something? Well, the point is that while you do pay a small penalty and inconvenience when you write the code, your job in maintaining it becomes much easier. And on balance, this is a huge benefit. Further, you'll discover that you don't need to understand as much about other people's code to be able to use it. And this makes it much easier to use the vast swathes of library code that Java includes. Another huge benefit to productivity. Let's start with a working project. This one is date2. We'll review what it does and then we'll discuss some changes that we might make to it. So the main method that we come into here creates a date object, and it sets the date so that it represents the 29th of February 2012. Let's take a look at the date class itself that was defined for this. The date class includes a day, a month, and a year fields. It also has the supporting structure necessary to provide a constructor that allows us to initialize those directly, and that is how we are constructing it here. So we construct new date with those fields, and that will invoke this constructor to do the initialization. Then, this particular one, we still have a call to increment the day field of meeting date. And of course, it's probably not a big surprise that when we run this, that will actually create a date of February 30th, 2012, which is clearly not valid. We'd also know that if we create this better meeting date object here and invoke the next day method, the next day method defined within that object specifies how to compute the next day even if there is a leap year involved and if there is February involved, or depending on how many days in the month there are. So this will always compute a correct next day. So what would be nice is if we could find a mechanism that prevented us from accidentally messing up the internal representation of a data structure. In other words, we really don't want to be allowed to arbitrarily increment day. Well, it turns out that this is actually quite simple to do. If we go to the top of our date class and we replace this keyword public with the word private, and we're going to do that for each of these fields, what that says is that the only place you are allowed to access this variable by its name is inside the most immediately enclosing curly braces. So that means all the code that is here, manipulating the days in the month and checking for leap years and deciding how to handle next day, can refer to this.day and can increment it and behave accordingly. But outside of the curly brace that starts here and ends here, we can't access that any longer. So let's go back to our program, and you'll notice that it's immediately thrown up a whole bunch of errors. Well, the first error, if we hover over here, says date has private access in date2.date, which is this class over here. What that's saying is you're not allowed to do that any longer. That's a good thing because it prevents us from accidentally manipulating this day field in a way that is inconsistent with its intended use. So we can no longer do this. The downside, however, is that we also can't access the fields day, month, and year to read the values inside the date. So the question then becomes, how can we print out the date? Clearly we need to be able to use these values to make this object useful. Well, there are a couple of ways we can go about this. If we look at the date class itself, what we could do is provide methods that give us access to read these values. If you think about it, being able to read the value is not damaging in this case. It's the manipulation of it without understanding the consequences of that manipulation that is dangerous. So when we want to add to the date, we would be forced to call this next day method. But when we want to read it, we could just have a method that says get the day, get the month, and get the year. And in fact, this idea of creating getter and setter methods, as they're called, or accessor methods, is sufficiently commonplace that there's actually a mechanism built into NetBeans for creating this code automatically. So if I right-click on the source window and come down to Insert Code, I can say Insert Getter Methods. It then offers me the question as to which of the fields I want to have getter access to. Well, I'm just going to select all of them, please, and then tell it to generate the code. And you'll see it's created these methods. They're publicly accessible methods called getDay, getMonth, and getYear. And this is actually a naming convention that says you take the name of the field, you capitalize the first letter, and you add the word get. And then all we do is it simply returns that to the caller. So now, if we save that one and come back to our program that uses it, all we need to do to print out this month would be to replace this reference directly to the variable element with get month and put the parentheses on so that that becomes a method invocation. And we've got one too many there. There we go. And then we need get day, and we put the parentheses in, and get year with a capital Y, and we put the parentheses in. And you'll see that now this is no longer complaining. So that gives us one means of actually accessing that date. Clearly, of course, we are no longer incrementing that meeting day, so we would probably need to say meeting date dot next day. And that way we will actually increment that correctly. If we choose to comment out this piece of code for the time being, toggle comment, we can actually run this. So if we save it and then run it, we should see that this version has now generated the correct date and has successfully printed out the date. But there's something else we can do with a date. What we're really saying when we add these methods for next day and similar things is that it is the responsibility of this class date to understand how to manipulate the variables within it. So is it not also reasonable to think that this class should know how to represent itself as text? And actually that is also an idea that is built into the Java language. It turns out that there is a method that the compiler can use to convert any object into a piece of text. And what that method is called toString. So let's inject into this a definition of a toString method. The essence of it is that we say it is public. When you're now beginning to realize that means we can access it from anywhere. It returns a string. Its name is toString with a capital S. It takes no arguments because it's going to turn this object into a string. Then we compute the string that we want to represent our result by adding this.month with a slash separator, this.day, another slash separator, and this.year, and we return it to the caller. Because this method is special and the compiler knows about it, there's a little bit more going on here than we necessarily know about right away. And because of this, we're going to put this little magic word in here, @override, and notice it's a capital O after the @ symbol. This is to do with the fact this method is special, but this isn't the right place to go into details. So now what we can do, if we come back to, let's first save that, and then we come back to our program code, I'm going to uncomment this line and then add to that, concatenate with the better meeting will be on string plus better meeting date. And I'm just going to put the semicolon on the end. Now remember, before what we did was to call bettermeetingdate.month and extract the value of the variable. We can't do that any longer because it's private. We could say .getMonth and use the behavior to get it. But what this amounts to is an automatic invocation of the toString method. So let's actually leave that toString in there. We'll save this and run it. And you'll see that now it prints out better meeting will be on 3/1/2012. And in fact, if we delete the explicit invocation of the toString method and run the code again, nothing changes. In other words, when the compiler needs to take any object and turn it into a string so that it can concatenate it with another string, it will call that toString method. There's one more question that we should look at now. What does static mean when it's applied to a method? And why did we have that on many methods that we've looked at up to this point, but now we're creating most of our methods without it? The essence of this issue is that the methods we're creating now are used in the context of a particular object, and as such, they don't use the keyword static. Methods that are used without being applied to a particular object must be labeled static. Static is a really odd word to use to make this distinction,
but that's been inherited from C++, the language that was a precursor to Java, so we're stuck with it. And there we have it. In this lesson, you've learned how to encapsulate the fields that describe the data in our data structures. Now we know that once those fields are inaccessible from outside of the data structure definition itself, or the class definition to use the proper term, we probably need to create other methods, like getter methods, to provide access to those values, and we'll create some methods which allow us to interact with the computational model, if you like, that this data structure or class now represents. In this lesson, we're going to look at some of the libraries that Java provides and the documentation that goes with it. Well-encapsulated objects are generally easier to use than libraries that consist of a bucket of loosely associated structures and functions that operate on them. The reason is that the object should take care of itself as much as possible. So with structures and functions, it's often unclear if there are rules about which fields of a structure are required for input to a function, and which will be provided as output from the function. Also, it's often unclear if you are supposed to invoke certain functions in a particular order, or if a function must be called to set up another one. While it's perfectly possible to have trouble understanding an object-oriented library, some libraries deal with intrinsically tricky issues, and some programmers create better libraries and better documentation than others. You should still find that in general, OO libraries are reasonably easy to understand. Like any software, names in OO are important. In an OO library, if you have an object called duck, it should be a model of a duck and nothing else. If the duck has a method called quack, then it should make the duck quack and nothing else. The duck should not fly away, nor eat, nor any other behavior. It should just quack. What this amounts to is that if you look at an OO library and you think that you have a good idea what something does based on its name, then there's a good chance you're right, and there's a good chance you'll be able to use it correctly. Let's start by looking at the documentation that Java provides. Point your browser at this link, http://docs.oracle.com/7/docs/API. Notice that this resulting window is split into 3 parts. In the top left is this list of all the packages available in the core Java distribution. Each package collects related classes that work together to solve a particular problem or family of problems. Some of them have suggestive names, such as java.io. Here you can probably guess that this relates to I/O operations, like reading and writing files. Some of the names are less obvious, like java.awt. This actually provides the Abstract Window Toolkit, which provides very basic tools for creating windowed interfaces with buttons and text areas and the like. Let's click on the java.lang package. That's here. This contains classes that are tightly tied to the language itself. Notice that the frame here in the bottom left corner just changed. This now lists all the elements that are part of the java.lang package. Let's click on string there. See that the frame on the right now shows the documentation for the string class. Most of the classes in Java will have a description of the class and perhaps even examples of how to use it in this top section. Though it's only fair to note that some classes are not well endowed in this respect. It varies with the programmer who created the class. As we scroll down, we come across a list of all the constructors for the class. There's constructor summary. So we see we can create an empty string, or we can create a string from an array of bytes, or an array of characters here, or perhaps as a copy of another string. This one here. There are a lot of these constructors, and many of them are actually quite rarely used. Scrolling down further, we find a list of the methods that are available for a string. Some of these are simple to understand and we'd be likely to use. Others are rather more obscure, and the chances are we wouldn't need them. So we can probably see what char@, might do, and similarly the compare_to method down here. But we might need to do a little more research to know how to, for example, use format. down here. And the matches method here. Further down still, we get a more detailed description of each of the constructors and methods that are listed. Clicking on the short description will actually take us directly to these longer descriptions, so we can see them immediately. There's also a section between the short and long descriptions. Methods inherited from something. Sometimes a class will have more than one group of these inherited methods. It turns out that object-oriented languages allow us to define a class in terms of another class with extras. That means we don't have to copy and paste a whole lot of code to create a new class that shares much of what an existing class provides. It also has some interesting consequences, since object-oriented languages consider that if one class is defined in terms of another class with extras, then we're allowed to substitute the class that has the extras in place of the original class. For example, if we created a class called person, and then said that the class VIP person is a person with extras, Java uses the syntax class VIP person extends person, then we can create an array of person objects and use it to store a mixture of both person and VIP person objects. This lesson doesn't intend to go into those details, but you'll need to understand that sometimes a method that you want to use might be defined in one of these methods inherited from sections. And it's okay to just go ahead and use those methods just as much as the ones that were defined in the class you started with. Before we wrap this lesson up, let's take a quick scan around and look at a few more samples of documentation for classes that you might want to use. Let's look at this integer class here. Notice that there is a method in here, parseInt. Passes the string argument as the signed decimal integer. If we look at this one in more detail, we'll see that it also says throws number format exception. Many methods might fail in certain situations, and the exception mechanism is how Java expresses that. We might also look at, in the math class, the random method. Let's click on this one. Returns a double value with positive sign greater than or equal to 0 and less than 1. So this one would allow us to create simulations that might be useful in games and so forth. Let's take a look at one more. We'll go to the java.io package and we'll look at the file reader class. And notice that we can create a file reader based on a string. And that says creates a file reader given the name of the file to read from. We can also see that a file reader provides, in the inherited methods, the ability to read. So we can read into a character array characters from a file. So, in this lesson we've considered how object-oriented libraries can be easy to use, and we've looked at the structure of Java's library documentation along with a few specific examples of useful functionality. In this lesson, we're going to look more closely at the difference between classes and objects, and at what is meant by static. We'll use a couple of examples that are in the project Objects Classes to illustrate these ideas. The quick answer to the first question, what's the difference between objects and classes, is that classes are the templates from which objects are created. So, consider a computational model of a customer. Clearly, if you're going to stay in business for long, you need multiple customers, and each needs a record in your computer system so that you can work with it. Each time you say new customer, Java creates a new object in memory. So here you can see we have created 3 individual customers. If it helps, you can think of this like a new structure instance. It's very similar to that. Or as a new row in a database. It's very similar to that too, except we can't search for it and it's in memory, not on disk. So, we will expect to create many customer objects while the program is running. Each object will represent a different customer. So, for example, one customer is named Fred, while another is named Jim, and the third is named Sheila. But each customer object was built from the same class, called customer. The class is the template that says each object must contain certain variables.
So in this example, we see that every customer has a name, an address, and a credit limit. It's the job of the customer class to specify that those fields must exist in every object that is created from this class. Each time that we want to get information about a particular customer, we need to have a handle on that particular customer. That's what our variable names are for. Customer C is a handle on the customer we created with the name of Sheila. That's rather obvious in one sense. If I had a meeting with 1,000 customers showing up and just yelled in the air, "Hey customer, what's your name?" nobody would know if they should answer or not. But if I walk up to one particular customer, shake their hand and say, "Welcome, I'm so glad you could come. What's your name?" I can expect a sensible answer. This is what happens when we prefix a method with a reference to a particular object. So here you see b.getName asks the question getName of the customer referred to by B. Many object-oriented programmers actually like to refer to this type of method invocation as sending a message to the object. Sometimes, however, we don't want to ask a question of a particular object. We want to ask something that is related to the class of objects. Consider, for example, that we are a salesperson wanting to go on a visit to some customers. We wouldn't phone one customer and ask them if there were other clients of ours nearby. Similarly, it would not make sense to code this as a method that would require us to send the message to a particular customer object. We might not even have any reference to any customer in the right area yet. Instead, what we do for our getCustomerNearAddress method that you see here is to label the method as static. And that makes it belong to the customer class rather than the individual objects. It's not something we ask a particular customer about. Notice here, we don't say b.getCustomersNearAddress, we say customer.getCustomerNearAddress. So in this way, we direct the message to the customer class as a whole using this special syntax customer.getCustomersNearAddress. It's important to realize that this is not a trivial method to implement. So you'll see here, we've actually just described the kind of thing that would need to be done. We would probably need the help of a database to achieve this one. In particular, the rest of this class, the way it's written, does not have any means of knowing about all the customers that we have. It's perfectly possible to code a class so that it does know that, but it has not happened here. The other thing that we must be clear about is that in each of these static methods, which are sometimes, by the way, called class methods, there is no this variable. We cannot refer to the fields of the current object, which is what this refers to, because there is no current object. We didn't direct this request to any particular object, so the compiler couldn't know what we meant if we referred to this.name, for example. Let's look at another example that works with a class called date. Each object of the date class represents a particular point on a calendar. You can see here we have a day, a month, and a year within this date. Consequently, most of the methods are not labeled as static. They must be invoked on a particular date object to work. So we have the getDay method, which will return the day in the particular date that this method was invoked on. We could just as well say this.day, and that means the same thing in this case. It's often a shorthand just to leave the this off and describe it in slightly briefer terms. But two of these methods are asking questions about things related to calendars, but not about a specific date object. Here, asking if a particular year is a leap year doesn't require a whole date, just a year. Asking how many days in a month there are doesn't require a particular date either, just a month and year that we're interested in. So we can mark these methods as static and invoke them in the context of a date class as a whole, rather than asking a particular date about something that is more general than that particular date itself. Notice what happens though if we try to change the reference to year to this.year. We get an error. The error says non-static variable this cannot be referenced from a static context. The compiler is making this complaint because there's no current this available, so it can't resolve this.year into anything meaningful. In addition to static methods, we can have static variables. In this case, you create one variable that will be related to the class as a whole, rather than getting a new variable every time you create a new object. An example of a static variable would be the maximum design speed of a particular type of car. Every Ferrari Testarossa, for example, has its own color, physical location, current speed, and amount of fuel in the tank. But the maximum design speed is 180 miles per hour. That's shared by all of them, and that would be a fair candidate for being a static variable. We could also use a static variable to keep account of the number of customer objects created. So here you see private static int count equals 0. Notice in this example how the count variable is incremented in the constructor. There is our public customer constructor. It may also be accessed by the static method getCustomerCount. There we say return count. Even though the static method can't use this to identify an element like the name or address, because we don't know which customer we're talking about, we can access static variables because they, like the static method, belong to the class, so we don't need this to find them. It's an interesting design decision as to whether a method or variable should be static or not. Generally, consider that if the method is operating on an object, or if the data are specific to the instance of the object, then whatever it is should not be static. But if it's a method doing general stuff related to the class as a whole, or if it represents data about the class as a whole, then it should be static. By the way, too many static items showing up in a program suggests that whoever wrote the code hasn't necessarily grasped the whole OO design thing very well yet. So, to wrap up, this lesson has considered the difference between objects and the classes that describe them. In this lesson, we're going to take a closer look at the package mechanism. The Java distribution has several thousand classes, and packages at their simplest are a way of grouping related classes together. This helps us to know where to look when trying to find functionality, and avoids us having to look through lots of irrelevant classes at the same time. Packages also define something called a namespace. A namespace is like a family name. At home, I might refer to my children by their first names, but in school, if I called one of them by name, 5 children might turn around. So I could use my family name as a way of reducing the confusion. Similarly, a class has a full name that consists of the package name and the name of the class. I can refer to a class using that full name at any time if I choose to. But much of the time, there's no name conflict, and I can get away with just using a short name. Let's look at an example. Here's a project called Packages. It has a main program file called packages.java, and that's the main method there that will start the code running. Let's take a moment to look at the Java API documentation. In the package java.util, here, we find a date class. This is a long-standing class that represents a date. Much of what it does has been superseded by another class called calendar, which knows all sorts of international calendars, but the date class suits our purposes well. I can refer to the date using its full name, which is java.util.date. And if I simply create an instance of it and print it out, let's put that code in here. Java.util.date today equals new, java.util.date. And then I can print the fellow out. I'll make sure it's saved and run that. And it says today is Friday, June 1st, blah, blah, blah. So we can see that it does something potentially useful. But using the full name of this class, this is sometimes referred to, by the way, as the fully qualified name, is rather cumbersome. It involves a lot of typing. It turns out that I can invite this class home and start just using the short name. This is like inviting one of my children's school friends home. I wouldn't use my children's full formal names at home, and I wouldn't use the full names of their friends either. Because I've invited them in, then as long as there's no obvious confusion, that is, they're not both called Jane, say, then the short name works well. So, to invite this class home, I have to tell the compiler about the invitation using this construction. I'm going to put this just in here. I say import java.util.date. This must be placed right after a package statement in the source file and before any class definition in that file. I can put multiple import statements in the file too. I'm not restricted to just one friend. Having done this, I no longer have to refer to the date class using its fully qualified name. I can use its short name. So I can change the variable type and the constructor to just use date, like that. Date today equals new date. And if I save it and run it, everything behaves exactly the same. Let's try deleting that import for a moment. So we'll take this and we'll cut it out. Notice the compiler is now complaining. If we hover over here, it says cannot find symbol for class date. There are actually several ways we could fix this. We could manually replace the import statement that we just deleted, but you'll find there are lots of classes you'll be using from other packages, and this manual typing can become tedious. So NetBeans has some suggestions. First up, we'll go to the source menu, click on that, and find Fix Imports. NetBeans can create the imports we need. In this case, however, you'll notice there are actually 4 classes in the system called date, and it's not clear which of those date classes we're referring to. NetBeans has actually made a guess because it saw us using this one just a moment ago. But this is as though there's more than one class at school with the name date, so we have to help NetBeans out by telling it which of these imports we want. So we'll choose java.util.date and we'll click OK. Notice it puts the import back for us. And that, of course, was the original point of the package and import mechanism. It allows us to deal with potentially conflicting naming. There are several date classes, each with different intentions. Because each lives in a different package or a different namespace, we can distinguish them, and yet, by using the appropriate import, we can write code that is concise. So when you use classes from other packages, whether those are packages you created or packages from libraries, you'll generally need to provide the import statements that resolve the fully qualified names of the classes that you're using. That raises an interesting question. We've used the string class, but we haven't ever imported it. That's because the java.lang package, which string belongs to, is treated as everybody's friend, so you never have to import any of the classes defined in it. Finally, you can create packages of your own to partition your own work. That's pretty easy, and NetBeans does most of it for us, though it's worth looking at the Java syntax that it creates to achieve this. Let's open up the packages project, and we'll find here the source packages element. Right-click on that, select New and Java Package. Give the package a name. By the way, package names should be entirely lowercase. So we'll call this Other Package, and then click Finish. Notice it created this other package here. These things are pictures of a brown paper parcel tied up with string. This one shows that it's empty by being gray. Now we can right-click on the new package and select New Java Class. We'll create a class here and we'll just call it My Class. Notice the naming convention for classes says that they should start with an uppercase letter as well as use an uppercase letter at the join in words. We'll click Finish. And now Other Package isn't empty any longer. We've got our class that's actually in there, and here we see the skeleton that's been created for us. Notice that right at the top of this skeleton there's this statement, Package Other Package. Turns out that's what puts this class in the Other Package package. From a syntax perspective, that's all that's needed. It's also true, though, that the source and binary files for this class must be located in a directory with the same name. But NetBeans has taken care of that for us. We'll give this class some minimal behavior just so that we can see that it's real. We're going to add a toString method to it so that it can print something out when we ask it to. Then we'll go back to our main program file and we'll add some code here to do something with this. So we create a class, myClass, and we create a variable to refer to it, and we ask to print it out. But notice that the compiler is complaining, cannot find symbol myClass. The point here, of course, is that it needs an import. We could do this the same way as before, but notice the little red blob here on the light bulb icon? Click on that and see that it offers us the option for add import for otherpackage.myClass. So we'll click on that, and it does precisely that and puts it up here. So that's another way of fixing a single import. You can choose whatever method you prefer. So there we have it. This lesson has looked at the significance of the package in Java, the use of import statements to allow us to use short names for classes, and how we can create our own packages and put classes into them.
Now that we've got to grips with some of the key pieces of Java, you know how to write procedural type code, you know how to do sequence, iteration, and selection, declare variables, and you've created some objects. Now we need to start learning a little bit more about some of the clever things that objects can do. If you've been around object-oriented programmers, you're almost certain to have heard them talk about inheritance and how powerful this can be. In a programming language, it turns out that inheritance has nothing to do with elderly relatives who die and are generous to you, but it's actually a mechanism that allows us to write code that is generalized in special ways. What we mean by generalized is probably best illustrated with an example. Imagine that you're writing a program that is going to deal with feeding of lots of animals in a zoo. You could write code for how to feed a lion. You could write code for how to feed a tiger. You could write code for how to feed the wolves or whatever else there might be in your zoo. But you end up with a lot of repetitive code where you're defining the same kinds of things over and over again. And in many cases, it might be that what you would do better to do is to describe each of those different types of creature in a generalized sense, an animal, and then write code that knows how to feed animals. In that way, you only have one piece of program code that deals with feeding, even though you may have many different types of animal, and perhaps might add more animals later on after the program was written as the zoo grows. Later in this part, we'll look at another two even more advanced concepts. There's the idea of an abstract class, and there's the idea of an interface. Think for a moment about the nature of an animal. In the program we just described for the zoo, we actually have a class called animal. But if we tried to create an animal, that would be a very strange beast indeed. It might have hair, it might not have hair, but there is nothing that is just an animal. An animal is a conceptual thing. It is, in fact, a generalization of real concrete things. Because of that, we don't really want to be able to have the program create an animal. We want the program to create lions and tigers, but think of them as animals. And an abstract class is suitable for just this purpose. You can define all sorts of useful features that are common to all animals, but you can't create one. Turns out that's not all you can do with an abstract class, but we'll leave the rest for when you get into the body of the lesson itself. Beyond an abstract class, there's a further notion called an interface. An interface allows you to specify only what something can do, but doesn't provide any implementation for it. That can be really valuable when you have capabilities that can be fulfilled in very different ways. Imagine, for example, taking a photograph. A person can take a photograph, but so can a spy satellite. And clearly, there's no common behavior or common foundation to those two things. They are very different, but you could use either of them for the purpose of taking a photograph. Interfaces are really useful for that kind of thing. It turns out that in real programming, you should probably use interfaces quite a lot. They're very flexible. They allow you to specify something in terms of that capability, but without having to get tied up with the implementation details. So with a little luck, once you have a grasp on what interfaces are and how to use them, you'll find yourself using them a great deal too. And then your Java code will be getting better and better by the minute.
In this lesson, we're going to look at one of the distinguishing features of an object-oriented language. This is the feature called inheritance. Let's start by taking a look at an example. This is the zoo project. Notice here is the main class of the zoo project. We come into the main method here, and the first thing this does is to create an instance of the class that it's a member of, this zoo class. You'll see that in the zoo class we have three variables, a sheep, a lion, and a zebra. We create instances of those, and that allows us to visit the zoo, where visiting the zoo prints out the message, you visit the zoo, and then prints out a series of messages as you interact with these animals. So we can feed the sheep, we can pet the sheep, we can feed the lion, which might be a little dangerous, we can pet the lion, which might be really dangerous, and we can similarly attempt to feed and pet the zebra. Let's take a look at the definitions of those classes. The zebra here says public void feed and just prints out a message that says what the zebra does when we do that, and it has a pet method. Similarly, the lion has a feed method and a pet method. It behaves slightly differently, and it's not a terribly good idea to go petting it. And similarly, the sheep, we can feed it and we can pet it. This is obviously one of those sheep that you find in the children's petting zoo because it's perfectly willing to be petted and thinks that you should give it more attention. Let's run this code and take a look at what happens. So there's the body of where things are going to get interesting. And we can see, you visit the zoo, you go to see the sheep, you try to feed it, sheep eats grass, munching happily. You try to pet the sheep, sheep pushes against your leg. So everything pretty much behaves as we would have expected it to. But notice how each animal has quite a bit in common. You can attempt to pet them, even in the unwise situation, and you can attempt to feed them. At a philosophical level, we can make a generalization about these creatures. They are all animals. Now, object-oriented languages allow us to express this generalization in the way we create our classes. So let's create a class that describes this generalization. We're going to call this class an animal. So I'm going to right-click on the zoo animals package, and I will say create new Java class, and I will call it animal. Now in the animal class, I'm going to put the same basic structure. We have a feed method, says the animal eats, and a pet method that says the animal gets petted. Now we can also make modifications to each of our three animal classes. Our zebra, we're going to say this extends animal. And for each of these methods, we're going to add the label @override. I'm going to do that for all three classes. Lion extends animal and @override and @override, and similarly sheep extends animal @override @override. We'll save all of those. Now what we've done is we've created a relationship. We are saying that, for example, a lion is a specialized form of animal. Now there's a lot of terminology you might come across here. We might say that animal is the generalization of lion, that animal is the parent class of lion, that animal is the base class of lion, or even that animal is the superclass of lion. Similarly, we might say that a lion is a child class, a derived class, a subclass, or a specialization of lion. Unfortunately, there's a lot of interchangeable terms to choose among. One important note here is that Java, like many but not all object-oriented languages, insists that there can only be one direct generalization for any one specialized class. That means you can extend one other class, although that class might in its turn extend something else. This is called single inheritance. Don't worry about it too much, but just know that our lion cannot extend both animal and carnivore classes, for example. Let's think again about this @override label. That tells the compiler that we intend that this method should replace an existing one in our parent class. That is, the class that we extend. This replacement process is called method overriding. It only works if the method's name
and the type and sequence of method arguments is identical. The return type must be the same too. There are some other rules, but this is not the place to get tangled up in them. So let's see what this code does. Everything is saved, and we'll go to our Zoo Java class and we'll run this. So it basically behaves exactly the same as it did before. Our sheep eats grass and munches happily and pushes against our leg and so forth. Let's just verify that we really did have behavior that we inherited into, say, the zebra from the animal before we did this override. Let's do this. We'll take this block and we will comment it all out. We'll save that. Notice there's no errors in here. There's no errors anywhere. Now when we run it, you'll see that we have the interaction with the sheep and we have the interactions with the lion. But then when we go to see the zebra, we try to feed it, it says animal eats and animal gets petted. So we really did get this behavior inherited into the zebra class for free. In our case, however, we actually don't want to inherit that original behavior. We do specifically want to replace it with behavior that is specific to a zebra. So we'll go back to that version of it, save the file. Now, so far, this just seems like a syntactic curiosity which might save us from cutting and pasting some code from time to time. But actually, we can do quite a lot more with this. Let's take a look at something we can do. We're going to switch into the original zoo class, and here where you see we have the private variables for the sheep, the lion, and the zebra, I'm actually going to create a new form of this. I'm going to say private animal array animals, and I'm going to initialize it with the sheep, the lion, and the zebra. Now it's complaining about the animal because it doesn't know what that is, but if I click on here, we can add the import for zoo animals. Now the other thing that I can do is that now that I have an array of animals, I can actually iterate over that array. So in effect, these two pieces are essentially equivalent. I have this version which works with the individual variables here, and this version which is working with the array of animals. And if I save that and run it, notice that if I double click on here, I can make this window a little bigger. First of all, we go through, we visit the zoo, we work on the individual variables, and then after we have attempted to feed the zebra the first time, or pet the zebra I think actually, we then come down and this is the output from the second part. It says we try to feed the animal. Sheep eats grass, munching happily. Try to pet the animal. Sheep pushes against your leg. So let's go back to the source code. You'll see that's where this is coming from. We're iterating over this array of animals and calling feed and calling pet methods on them. Now there's something important going on here. Although the compiler sees us invoking methods feed and pet on an animal object, the behavior we see is the behavior of the actual animals, lion, zebra, and sheep. This is important. What we get is the behavior of the actual object at runtime, not the behavior that the compiler might have expected from doing a static analysis of the source code. This is called dynamic invocation or late binding. It's a critical feature of method overriding that's going on here. Notice that we are effectively able to substitute our derived classes, lion, sheep, zebra, for the generalized class animal. We did this and used an array of animal to hold the individual animals, and we can do this with method arguments too. Notice that I can create a special method, and this one says visit animal, and it takes an animal as an argument. Now, in my loop here, I can replace this lot with a simple call to visit animals for animal I. Just to clarify this code a little, I'm going to comment this block out. So now we'll just see the one set of visits that we get when we visit the animals in the array. In fact, having done that, I can comment these variables out because I'm not using them at all now. Save the code and run it. And we should see that we get try to feed the animal, sheep eats grass, munching happily. So it's exactly the same as it was before,
what we've been able to do is to write a method that works on an animal and then pass in a particular animal, whether it be a sheep, a lion, or a zebra, taken out of that array, and behave accordingly. So this method knows nothing about sheep, lions, or zebras. It only knows about animals, and yet it works perfectly satisfactorily with actual animal implementations. So, in this lesson, we've taken a first look at the inheritance concept and its implementation in Java syntax. With a little luck, you can see that this mechanism can help us create generalized code that is more flexible than it might otherwise be. For example, we could create a tax calculator method that takes a taxpayer as its argument, and that taxpayer could actually be a person or a corporation, and the method works correctly using behavior from the taxpayer itself when necessary to distinguish the particular type of tax is owed. In this lesson, we're going to take a little closer look at the inheritance concept and see what additional tools the Java programming language provides. Let's consider the Zoo2 project. Here is the main class of that. It has a main method which creates an instance of the zoo class. That's this one. Inside the zoo class we have an array of animal object called animals. The contents of that array are a sheep, a lion, and a zebra. Then when we have created our zoo object, we call z.visit. And we go to take a visit to the zoo, print out a message to that effect, and then we iterate over the contents of that animals array and visit each animal in turn. Then we print out that we're going to feed it, and we feed it, and we print out that we're going to pet it, and we pet it. So each of these animals is a subclass of this base class called animal, which has a feed method and a pet method, and then the individual animals like lion override that feed and the pet method and provide their own behavior. But what does an animal actually look like? It's not really a thing, is it? It's more of a concept. You wouldn't see an animal running around in the wild. You'd see a particular animal, like a lion, a sheep, or a zebra. Java actually allows us to express that. It turns out we can mark the animal class as abstract. So we can say public abstract class animal. The first thing that this does is to actually prevent us from ever creating an instance of an animal directly. So if we go across to our zoo class and we were to attempt to add into here new animal, we'll see that we get an error out of that. Zoos animals animal is abstract and cannot be instantiated. Well, that's actually quite a good thing, isn't it? Because it wouldn't make any sense. What would it look like? So that allows us to prevent ever creating an instance of that. Well, this idea actually goes a little further. Because if we think about it, what would it mean to feed an animal? Just a generalized animal as opposed to the specific feeding of a lion or the feeding of a sheep. Well, it turns out we can take this idea a little further, and we can say that although an animal can definitely be fed, it makes no sense to feed the abstract concept of an animal only to feed the concrete specific animals, the lion, the sheep, and the zebra. The way we can do that is we take out the body of the method, we replace it with a semicolon, and then we add this keyword abstract again into the method. We can do that for both of these. Abstract, and then remove that and replace it with a semicolon. We'll save that, and we'll go back to our main class. You'll see there are no errors, no complaints anywhere, and if we run it, it does exactly what it's always done. So everything still works, and it's not a problem to implement our zoo as an array of animals, even though animal is not a real thing, it's just an abstract concept. Now there is a feature of abstract classes that we haven't gone into detail on. That is that they do not have to have abstract methods. They can have as many or as few real methods, and as many or as few abstract methods as you like. They can have variables for storage too. So if there's some behavior in the generalization that is concrete and shared, you can put that right there once in the abstract base class, and all the specializations will inherit that behavior automatically. Java actually allows us to take this concept a step further. Sometimes a class is entirely abstract with no variables and no concrete methods, only abstract ones, just like our animal is at the moment. In that case, it might be appropriate to turn the class into something called an interface. An interface is really just that, an entirely abstract class with only abstract method declarations and no variables. So let's go ahead and make that change. We'll change this class to be public interface animal. So we lose the keyword abstract and class and replace it with interface. Now for each of these subclasses, we no longer say extends animal, we say implements animal. And we'll save that one, and then we'll replace here, and save it again, and replace here, and save it again. Notice everything else is happy. We still have our overrides. We still provide the concrete method here. And animal is happy. Lion is happy. And the zoo class is happy. So if we run this again, we see that we get the exact same behavior we got before. So why interfaces? Well, recall that we were only allowed to have one parent class. It turns out that Java does allow us to implement multiple interfaces. So if we want to describe our lion as being an animal and being carnivore, that's fine if both animal and carnivore are interfaces. Actually, either one of them could be a class, just not both. You can extend one class and any number of interfaces. So as a final thought, we've created two string methods on classes and labeled them as @override. But the classes that we did that to didn't have any extends in them. So what parent class method were we overriding? Well, it turns out that if we don't say extends something, we're automatically made a subclass of a special class called java.lang.object. And that's the class that has the toString method that we've overridden. So in this lesson, we looked at abstract classes and interfaces, and we saw how we can use those to provide specializations that don't necessarily include any or even all of the behavior as concrete implementations.
Your Java programming skills are really beginning to come on pretty strong now. You're handling things like objects and inheritance, and underneath it, of course, you've got all the basic mechanisms for handling regular program logic. The next thing we're going to look at is how you might get large amounts of data into a program so that you can operate on that data, and indeed get that data back out again. That is, we're going to look at I/O. I/O, of course, input-output, is the mechanism we'll use to read data from files and write data out to files. Because of the generalization mechanisms that we've seen in object-oriented languages, Java is going to actually allow us to use the same basic mechanisms for reading and writing files and for reading and writing the keyboard. Indeed, later we're going to find that we get another pleasant surprise, and we'll discover that the I/O operations we'll look at here can actually be reused through generalization for something else. It'll be fun when we get to it. Whenever a program interacts with things outside of itself, it's possible for something environmental to go wrong. For example, we might tell the program to read a particular file, but the file isn't there because we spelt the name wrong. Any of this type of problem, where the program is expecting one thing to happen, but something doesn't happen the way it should, can be tricky to handle in a programming language. Java handles this kind of thing using a mechanism called exceptions. The nice thing about exceptions is that they allow us to write the program code initially as though everything is going to work perfectly. The exception mechanism is intended to allow us to write our code for what we call the happy path, that is to say, what happens when everything works properly, all in one neat block without cluttering it up with how we're going to deal with things that go wrong. Similarly, it's going to allow us to put
code that describes how to handle when this goes wrong in one place, separate from the happy path. And then we can also put what to do when that goes wrong, assuming there's more than one problem that might arise. Again, all the code together in one place, but separate from the other two, the happy path and the first problem. This will allow us to write code that is robust in the face of failure and yet isn't cluttered up. And that's going to be a good thing when you have a large and complicated program with lots of potential for both internal and external problems. In this lesson, we're going to learn some basics of the I/O libraries that Java provides. Along the way, we'll learn just a little about the exception mechanism, which gives control of how error situations are handled. Java handles I/O operations in two different flavors. We can handle 8-bit data, and we can handle textual data. Textual data is represented using a 16-bit Unicode character set. That's why the char is an unsigned 16-bit number. Java seeks to generalize its handling of all I/O, and in so doing it comes up with 4 core abstract classes on which much of the rest of the I/O libraries are built. 2 of these classes are input stream and output stream. These handle 8-bit data, and as the name suggests, one provides for reading data in, while the other provides for writing data out of a program. The other 2 core abstract classes are reader and writer. These handle character data, 16-bit Unicode, and as their names suggest, reader provides for input and writer provides for output. You can find documentation on these classes in the regular Java documentation. So let's look at these in the standard Java API documentation. Start in this corner and scroll down until you find java.io. Then you can click on the java.io package name here and see a list of the basic classes available to you in java.io. Here you see input stream. It says this abstract class is the superclass of all classes representing an input stream of bytes. We also see reader, abstract class for reading character streams. Because these are abstract classes, we know that there must be some concrete subclasses that provide real usable behavior. So it's not a big surprise that we can find the file reader class, which describes itself as a convenience class for reading character files. We can find that one here. If we scroll down and look at the classes, file reader, click on that. There we go, convenience class for reading character files. It has a constructor that will take a string describing a file name to tell it what file to open. We can also find a buffered reader class. This one notes that it reads text from a character input stream, which means another reader, by the way, buffering characters so as to provide for efficient reading of characters. It's long been recognized that I/O should always be done in the biggest chunks possible so that you get the best possible performance. That's an interesting idea. If you follow the logic, the idea is that you can attach one reader to read from another reader. That's kind of a neat idea and allows the combination of certain types of processing, like buffering, to be combined without having to create special classes for each combination. But there's actually another really good reason for using a buffered reader, and that is because the buffered reader provides a handy readLine method. See if we can find that one. Scroll down in here, look at the methods, and we will see readLine, reads a line of text. None of the other readers do this, so without it we'd be stuck reading one character at a time or perhaps reading a chunk of data into a char array. Let's see if we can make this thing do something useful. I've just created this project reader file as a starting point. And the plan is we're going to make this read some lines of text from a file and print them out. So this is just the empty skeleton that was created for me by NetBeans, and I'm going to put some code in here that I'm hoping might do something useful. So here's what I'm doing. I'm creating a new file reader based on a particular file name, and I'm storing that in a variable of type file reader, and then I'm attaching a new buffered reader to connect to the file reader and storing the variable that refers to the buffered reader as BR.
Then what I do is I work into a loop where I declare a variable called line of type string, and I say read a line from the buffered reader and store it in that variable. And then if that's not null, we go through this while loop and we print out the line that was just read. Well, I'm going to need some imports, so I will do source fix imports, and we'll notice that it imports java.io.bufferedReader and FileReader. Unfortunately, the compiler is still complaining about something. So let's hover over this error and see what it says. Unreported exception, java.io.filenotfound exception, must be caught or declared to be thrown. This one down here says unreported exception, java.io.io exception, must be caught or declared to be thrown. At its most basic, this tells us that the compiler is worried that these two elements, the constructor of the file reader and the readLine method, might break in some way. That's reasonable. If we try to open a file that doesn't exist, clearly that won't work. And if we try to keep reading past the end of the file, that's probably going to cause trouble too. But what's perhaps a little odd about this is that we can't just ignore the error and hope it doesn't happen. Java, in the interests of good quality software, does not let us ignore these problems. We have to do one of two things. We can either allow the problem to break our method and effectively pass the problem to our caller, or we have to try to do something about it. Well, in this case, we really don't care, as this is not production quality code. It's just meant to be a little example of how to use a file reader and a buffered reader. So, we can simply tell the caller of this method that it might break. There's a quick and dirty way to do this, which is to label the method itself, here the main method, as throws throwable. When we add this element, what we're doing is warning the caller that this might not work and that it should probably be ready to handle the problem. Well, the caller in this case is the Java virtual machine that's running our program. So what will happen is if it fails, it will just stop the whole program. Not a problem in this case. Anyway, let's save that and run it and see what happens. Well, it does indeed break. That, of course, is because there's no file test.txt. Notice here we attempt to open that file for reading, and we haven't done anything to create that file. The error is actually quite descriptive. It says exception in main thread, java.io.filenotfound exception, test.txt, no such file or directory. And it even tells us that it occurs in readerfile.java at line 21. So it's pretty descriptive of what's gone wrong. And it turns out that a java.io.filenotfound exception is actually an object that has been thrown, and that's what's trying to describe the problem. There's a lot more to know about exceptions, in particular how we can recover from problems that they represent. But this is not the lesson to discuss that, so we're going to let that go for now. Anyway, let's create the text file. So to create that file, we're going to right-click on the project, say New, and we'll come down to Other. We'll select Other here, come down here, and scroll down and find Empty File. We'll click on Next, and then we'll say text.txt and hit Finish. Then we can type some text into here and save everything. And as we come back to our main program, we can run that, and we see that this time it actually works. It reads the lines of text, prints them out. We can see that they came from here because they're prefixed by the read colon and a space. So this lesson has given a basic introduction to using Java's I/O libraries, and we've started to see how problems are represented in a Java environment using exceptions, and one way that we can deal with what happens when an exception arises. In this lesson, we're going to investigate Java's exception handling mechanism. Exceptions are the way that Java reports error situations, and the mechanism allows us to create code that controls our program's response to those errors. We'll use this project, readerfile1, and build on that. Right now, the program attempts to read a file, text.txt, and print the lines out onto the console.
in this loop. If the file doesn't exist, or if there's a problem like a damaged disk during the reading, then the program just quits. We've labeled the main method as throws throwable. That's a crude way of saying when bad things happen, just give up. You shouldn't do that in a production program, but it's great for learning from. Well, the first thing that we might want to do to improve this is to take control of what happens when the file is not found. Java gives us control of exceptions using a try block. Let's start by taking out this throws throwable part and see where that takes us. Immediately, the compiler complains about the 2 lines that might fail. Let's click on this red error blob and see what it says. Hovering, it just says unreported exception, java.io.filenotfound exception. But when we click on it, it offers surround statement with try catch. Let's go ahead and try that. See what it's done. It's created this block around this statement that could fail that says try, and then goes into the curly braces, and then it says catch file not found exception. Remember, that was the exception that it was saying might go wrong here. And then inside the catch block, it has this rather ugly looking logger.getLogger blah 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 .log, which you can probably guess is going to attempt to send a log message to report what went wrong. Well, we're not really interested in some ugly log message, though we'll leave it in place for the time being. What we probably want to do is to send an error message out to the console that we can actually read. That log message might do something similar, as it turns out. But let's say system.err.println file was not found. Now, we've looked at system.out many times, but system.err is actually the system's error channel. It'll just show up on the console in NetBeans in red, but other than that it's the same. And if you wanted to, you could have said system.out just as easily. Well, there's another problem, look, down here. This one is now saying variable fr might not have been initialized. Well, that is because fr gets initialized in here where we say fr equals new file reader. Unfortunately, up here, there's no initial value for it. So what we'll do is say equals null. That should make that problem go away. Let's actually move this buffered reader constructor inside the try block. That actually causes another problem. Notice down here, this BR, which should be that one, isn't found. This is quite a common situation when you have try-catch blocks. If you declare the variable outside the try-catch block, then it's in scope beyond the try-catch block. But if you declare it inside the try-catch block, then it isn't. So this is only visible between the enclosing curly braces. So what we'll need to do is to take the declaration outside and change that so that it's not a declaration. And again, we see variable might not have been initialized. So we'll set this to equals null. The point, of course, is that if this statement explodes and creates this exception, then we'll actually end up out here after we've caught the exception, and we won't actually have ever set either of these values potentially. And the compiler is very fussy about knowing that things have been initialized. Well, the other problem is we have this potential exception down here as well. And this one says unreported I/O exception. That just means things can go wrong sometimes when I/O is happening. So for example, if the disk was corrupted, then it might have managed to open the file, but it fails partway through reading it. Let's click on this thing again, and we'll say surround statement with try catch. And this time you'll notice it's surrounded the entire while loop, because that's one statement, with try catch. And we've got, again, this rather ugly logging message. Well, we'll go with that for the time being. That's not a huge problem. Now we don't seem to have any complaints from the compiler any longer. So let's give this one a try. We will save it, and then we'll run it. And it seems to work again. This time, let's see what happens if we change the name of the file we're trying to open. We'll just change it to something that doesn't exist. The only file that exists in this project is currently called text.txt, and so there's nothing called non-text. So if we run it again, this time we get a whole bunch of red output, and you'll notice the very first line says file was not found. And that's the error message we created there. Then immediately afterwards we get the output of this logging message, which you can see is a little bit more verbose, not necessarily more helpful, but it does explicitly say non-text.txt, no such file or directory, and then the body of the exception tells us the line that the error occurred at, and so forth. Interestingly, it carried on after it ran the catch block, and it actually also failed here when it discovered that BR was still null. And so that causes a null pointer exception. 2 exceptions in one program run. It's pretty good going. Let's review briefly what's happened so far. The compiler knows that the constructor of a file reader might fail and might throw an exception. Because of that, we are forced to surround that with a try block and to have a catch block that names that exception, or possibly something more generalized, and this catch block will be invoked if this exception arises at this point. So there's a couple of paths through here. The first is we come down, we hit the try block, we create the file reader, it works, we create the buffered reader, and then we'll carry on from here, having not run the catch block. The other possibility is that we construct the file reader and it fails. That throws this file not found exception, so the execution jumps straight from here into here, prints out this message, prints out this rather complicated logging message, and then carries on. As far as Java is concerned, if you catch an exception, it assumes that you fixed the problem, and it will carry on after the catch block. Because of that, therefore, it goes into here, goes into this try block, and then this try block actually has a null pointer exception in this case because BR was never set up. That isn't really what's supposed to be going on there, so that's not of prime importance to us. So we have 2 possibilities. No exception arises, we run through the try block, we ignore all the catch blocks, we continue. The other possibility is somewhere in the try block, the exception arises, it skips into a catch block that names the type of exception we're interested in, it handles the catch block, and then it carries on afterwards. Well, clearly, this kind of exception handling, really just logging the error and then failing anyway, isn't terribly useful in the real world. What we'd like to be able to do is to go round and try again. So one of the classic situations we'll end up with is that we need to build a loop around this attempt to read something. We're going to build that by attempting to read something from the keyboard, so that way we can keep giving different file names, and each different file name can cause it to fail or succeed accordingly. The way we read the keyboard is like this. We start by creating an input stream reader attached to system.in. System.in, as you can probably guess, you've seen system.out and know that sends output to the console. System.in reads from the keyboard. Unfortunately, it reads the 8-bit characters in whatever the platform's native character encoding is, and Java wants to work with 16-bit Unicode characters. So what we do is we attach this thing called an input stream reader onto our keyboard input. Input stream reader takes 8-bit characters in whatever the local platform encoding is and turns them into 16-bit Unicode characters. And of course, it's a reader interface that allows us to read characters in the usual way. But we want to be able to read a line at a time, so we attach a buffered reader onto the input stream reader. Now we have this buffered reader that we're calling keyboard that will allow us to read from the keyboard a line at a time in proper Unicode characters. The next thing we'll need to do is to build a loop around the whole attempt to open the file. In order to control that loop, we're going to need a variable, a flag that says success is false initially. So the idea is we start out with this flag set to false, and as and when we've succeeded in opening the file for reading, then we'll set it to true, and that will stop our loop from going round and round and round. So I'm going to replace this with a loop that will allow us to go round and attempt to read this file. So here you'll see we say while not success. Remember that exclamation mark symbol is Java's way of saying not. So while we have not succeeded, we'll print out this message to say enter the file name, and then we have a declaration of a variable that we'll use to hold the file name we've attempted to read. Then in our try block, we've got a slightly modified behavior here. We read from the keyboard one line and we save that as this file name. Then we attempt to construct the file reader based no longer on constant text, but on the file name we just read. If that works, we carry on and attempt to create the buffered reader. If we're still successful at this point, then we set our success flag to true. If, however, our attempt to read the keyboard fails, this actually can throw an exception, as it turns out, and what that would be a general I/O exception. So there's a catch block for the general I/O exception that says failed to read the keyboard. It's fairly unlikely that'll happen. The other possibility is that the attempt to create the file reader failed because we still didn't have the right file name in there. For that, there's a catch block that catches the file not found exception, and that prints out file name was not found, try again. Now at this point, I actually want to finish that loop, so we'll put the closing curly brace in, reformat the code. Now there's a couple of observations to be made here. The first is we actually now have two catch blocks because there's two things that might go wrong in what would otherwise be our happy path. So if everything works, we come into the try block, we execute each of these 4 lines, that sets the success flag to true. We carry on after the end of the catch blocks, which takes us to the loop, and the loop then terminates because success is now true. However, if the keyboard read fails, it throws an I/O exception and comes in here. If the file reader construction fails, it throws a file not found exception and jumps in here. One thing that's important to know is that file not found exception is actually a specialization, a subclass of I/O exception, which means that if we didn't have this catch file not found exception block, we'd actually jump into this exception handler anyway. Because this is more specific than this one though, if we put this as a catch block first, we can catch just that exception here, and any other kinds of I/O exception will be handled here. If we tried to put these in the wrong order, the compiler would complain because it would point out that everything was going to hit the first exception handler that matched, the I/O exception handler, and that the file not found exception would never catch anything if it was underneath. Think of these exceptions as being thrown up and then they drop down into the first available handler that matches them. So now let's try running this one. We'll make sure it's saved and we run it. It says enter file name. We bring the focus down in here and we'll say rot. File was not found. Try again. And then we say text.txt and it goes ahead. All this succeeds, sets the success flag to true. That causes the termination of the loop. And then it comes down into the same piece we had before, where it reads the lines one at a time and prints them out. So there we have it, a quick overview of Java's exception handling mechanism. There is more to know. Notably, there's a finally block that could be placed in here, but this isn't the lesson to discuss those.
You're really starting to get well into Java now. You can build things that have complex algorithms. You can have complex representations of real-world things protected through encapsulation. We can also handle files to store our data, both for input and for output. And we can write code that handles exceptions so that when things go wrong, we both have program code that is nicely organized and therefore a resulting program that is likely to behave well in the face of that problem. The big piece that's missing that we still need to fill in is how to build a graphical user interface. You've probably noticed that so far what we've been doing has been command line based, and real users aren't that keen on command lines. There are lots of different ways of building a graphical user interface in Java,
but one of the primary core ways that is provided with the Java toolkit is a mechanism called swing. Swing is just a fancy name. It doesn't have any special meaning, but swing is the toolkit that most people will use to build graphical user interfaces in Java. It has a very rich set of tools for things like text fields, buttons, menus. They're all there. It can work with complex graphics if you choose to, though we won't be getting into that much detail this time. Because it's so big and complicated, of course, we can only look at a limited subset of the facilities that Swing provides, but you're still going to see that in remarkably little code, we can create a very real user interface for a program. There are several things that have to happen to build a graphical user interface for a program. First of all, you actually have to be able to create the widgets, as they're usually called, things like buttons and so forth. You have to be able to put them on the screen in the place you want to put them, and you have to be able to write code that allows your program to do something when something happens to that button because of what the user did. Java uses a pretty standard mechanism, sometimes called event handling, sometimes called callbacks, to allow you to attach your code to those components, things like buttons and so forth, in a way that allows your code to be invoked by the system when the user interacts with the things on the screen. Positioning components in a Java graphical user interface is a little more interesting than perhaps some other languages. Because Java runs on so many different platforms, you can't simply do positioning in terms of pixels. If you think about it, you don't know what font will be being used or how many pixels it will take up, nor do you know when you write the program how big the screen will be or even what colors are going to be available to you. Because of this, Java has a special mechanism for deciding where to put things on the screen. Instead of specifying that you want this button, say, 10 pixels across and 25 pixels down, you'll describe it according to some kind of principle for layout. So you might say, I want this in the top left-hand corner, and then I want that to be next to it. These are things called layout managers that govern the way this setup is done. We're going to show you how to do that so that your graphical user interfaces can work in a fashion that is platform independent. That is, they'll work properly no matter what platform you're running Java on when that program is executed. So far, this is all sounding very powerful, very easy, and it is. Unfortunately, there's one aspect of building a graphical user interface which can be a little bit tricky. It is usually necessary to ensure that the access to those elements of our graphical user interface is only made through one thread. There is one particular thread of execution that is in charge of everything in the windowing system. And because of that, because we have our own program code running in a different thread, we have to be able to coordinate the operations that are going on in what's called the main thread, which is code that we wrote doing general work, with the operations that are happening in what's called the AWT thread, which stands for Abstract Window Toolkit thread, or sometimes known as the event thread. We don't want them to mess with each other's data structures. That would cause corruption and the program would crash or fail in some horrible way. What we need is to make sure that each piece is responsible for its own work and they communicate tidily. Well, that probably all sounds a bit daunting, and it probably should, because if you know anything about threading from any previous environments, it can cause some very strange failures. Well, the nice thing for us is that Swing has a little toolkit that makes this a lot easier. So we'll show you the techniques you can use to ensure that your code behaves properly, as simply as possible, and is reliable and robust. So by the time we're done with this part, you will be creating very real programs, implementing your algorithms, protecting your data with encapsulation. You'll be handling file access. You'll be writing exception code to handle problems that arise at runtime. And you'll have elegant, full-featured user interfaces attached to them.
In this lesson, we'll look at some foundations of creating graphical user interfaces in Java. There are actually 3 popular libraries for creating GUIs in Java, but we'll restrict ourselves to one called Swing.
This is a really powerful, fully featured GUI toolkit, so of course we'll only be scratching the surface of what it can do. It's also a part of the core Java SE distribution, so you'll know it's available to you. In a Java GUI, almost everything that's visible on the screen is a component. A component might be a button or a text area or a drop-down list, for example. But there's also a special kind of component called a container. The job of a container is to hold other components. But since a container actually is a component, we can put containers inside containers too. That way we can build GUI layouts that have nicely organized regions, and even build pluggable interfaces that would allow us to reuse a part of the GUI in another program if we wanted to. That's actually one of two founding principles on which GUIs are built. If you're interested, that one's based on a design pattern called composite. There's another principle, which is that since Java is platform independent, we cannot make assumptions about the pixel dimensions of anything in our GUI. Instead, we have to describe things in a relative way and let the system work out how best to present the components. To support this idea, there's an interface called Layout Manager. This interface is implemented by several concrete classes that offer different ways of describing a layout. We'll look at one of these, called a grid layout, in just a moment. So let's dive into building some real code and see what it does. We're going to look at this project called GUI1. The first thing we'll need to do is to actually create a top-level container called a JFrame. We're going to need an import for that. A JFrame is the top-level window that will have the controls, like these up here, surrounding it. But if we simply create this, this is just an object in memory, and the system has no way of knowing that we actually want to have this visible on the screen. After all, we could have a situation in which some piece of our graphical user interface is hidden for a while and pops up in response to a user doing something. So the system can't just assume that we want it visible immediately. The way we'd make it visible is actually to call a method on the JFrame that says setVisibleTrue. You can probably guess that if we said setVisibleFalse, it would make the frame disappear. Well, it turns out if we run this by itself, it's still not going to be terribly useful because that frame is probably going to be infinitely small, so we might actually just not see it at all. What we need to do before we make it visible is to actually give it a size. There are several ways to give a component like this a size, but the one we're going to use is actually somewhat cheating. We're going to use absolute dimensions for its boundaries. So what we do is we call this method setBounds, and we tell it we want the top left corner 10 pixels in and 10 pixels down, and we want its width to be 300 pixels and its height to be 200 pixels. Remember what I said about not really being a good thing to use pixel dimensions, but for now, this is a good way of setting our top-level window. So if we save that and run it, we'll notice that this empty frame pops up here. Drag it down into the middle. There's nothing in it. I can resize it, and it has a title bar at the top. That, you'll notice, is the same title bar that we specified in here when we created it. There's something a little interesting about this, though. If we click on the close button, the program is still running. Notice the little red box here, that's the stop button that we can use to deliberately and manually kill a program, and it still says run. So let's kill it, and it finally says build stop, and see what we can do to fix that. The issue here is that it's not fair to assume that just because we click that close button, we want to kill the entire program. There are other possibilities. We might just be closing this window. So the way this GUI system is set up, it doesn't make any assumptions of that sort, but we can tell it what we want it to do. So the way that we can tell it, there is a convenient method, setDefaultClose operation. And there are several possibilities for what we might do when we click that close, but what we want to do is to cause the JVM to actually exit. So we call this method setDefaultClose operation, and we give it the parameter JFrame exit on close. So let's save that again and run it. And we should see now that if we click on the close button, it does in fact complete the execution of the program. It's no longer running, the little red button's gone away, and it says build successful. So that's a step forward. The next thing we'd like to do with our program is to actually add a little bit more behavior to it. And as we said before, we can't go sticking components at specific pixel dimensions and expect things to work well. So the very first thing we're going to have to do is decide on a layout manager that we're going to use with this. Well, probably the simplest one to use is one called a grid layout. We'll get the import for that. A grid layout assumes that you will divide the area of your window into exactly equal sized rows and columns. We can specify the number of rows and the number of columns when we create the grid layout. What will then happen is as we add components to this container, the J-frame, it will put them first in the top left and then moving to the right along the row, and then it will move down onto the next row and add them like that. Well, this one is going to be 2 by 2 components, so there will be 2 cells widthwise and 2 cells vertically, so we'll have 4 cells in total. The next thing we'll need to do is actually add a component to it. So we'll have to create the component and then add it to the layout. So the way we can do that is first we create a button. So we declare a variable JButtonB and create it, new JButton. The text in the argument to the constructor will be the label. Let's get the import for that. And then we tell the JFrame that we want to add that component, the button. Let's save that and run it. Notice that we now have this button and we can click on it. The layout manager has gotten slightly confused because we told it we wanted 2 rows and 2 columns, but then we only gave it 1 component. So it made its best guess. We'll find in a moment or two as we add more components that the layout will behave as a 2 by 2 grid like we told it to. Let's go ahead and add a bunch more components to complete that grid. So we've added quite a lot of stuff here and we'll need some imports. So let's take a look at what we've now got. We have our original button that we create here. Then we create a component called a text field that we add here. And we give this text some initial text, edit this. A text field is a single line text component. Then we create a JPanel. A JPanel is actually another container. The plan is going to be that we're going to put into that container 3 more components, these JRadio buttons. Each JRadio button has a label, English, Francais. Notice here we use a Unicode literal for the C with a little curly thing underneath it that they call a cedilla. That's the hexadecimal code E7, and Deutsch. In the case where we create the radio button with the second argument true, that one says this one should already be selected. Of course, radio buttons have a special behavior that when you press one, the others pop out. And you might have multiple collections of radio buttons on one graphical user interface, and you don't want them all to pop out if they're in sets. So the way we tell them what set they belong to is to create this thing called a button group and add each of those JRadio buttons to the button group. Now, all the buttons in this button group, if you push one of them, it will automatically unpush the others. Inside the panel, we're going to present these 3 radio buttons. And the way we need to do that, of course, is first to set a layout manager. So we set a layout manager using the grid layout, which has 3 rows and 1 column. And then we add each of those radio buttons into the panel. The next thing we do, we create an array of 3 strings and another component called a JList based on those labels. So then what we do is we add our button to the JFrame, followed by our text field to the JFrame, our panel to the JFrame, and remember this panel already contains other components, and our list to the JFrame. Then we still have our set default close operation, our bounds, and our set visible. So let's save this and run it. So now you can see our button has moved into the top left corner, and we can still click on it. Our text field allows us to enter text here. It is a single line text field. We could use a text area instead if we wanted to have multiple lines. And then our radio buttons, all 3 of them appear in this one cell. But remember that we said that they are actually in a panel. The panel really doesn't show up. It's just a placeholder component. And because of the group that we added them to, when we click one, the others unclick automatically. And then we have this list component, which again presents within that one cell and offers multiple options within it that we can click on. So there we have it. Our graphical user interface is constructed using a top-level container, almost always a JFrame. That will have a layout manager which decides how components are positioned on that layout. And the grid layout is a nice, easy one to use. It's not terribly imaginative or very pretty. It always sets things out so that the vertical and horizontal space is divided equally based on the number of rows and columns you specify. Then we created a J button and a J text field. Those are nice simple components. Then we created our J panel and put several radio buttons into it. We also put the radio buttons into a logical group so that only one of them would be checked at a time. We ensured that the layout of those radio buttons were 3 rows and 1 column so that those within the panel would lay out nicely. Then we created our JList with 3 text labels in there and added the whole lot to the JFrame. Set our close operation so that the program will stop when we press the close button, gave it a physical size and position on the screen, and finally made it visible. In this lesson, we're going to learn how to attach behavior to graphical user interface components. To invoke programmer-specified behavior when a user interacts with a component in a Java GUI, we use an approach known as a callback. To make this happen, we write our code in a class that implements a predefined interface and then give the component an instance of the class with the instructions, when such and such happens, please call the something or other method in this object. In this example, such and such can be any of the user interactions, such as typing a character in a text field or clicking on a button, and the something or other methods have all been predefined for the particular user interactions. Let's get a little more specific. One very common user behavior is clicking on a button. We'll implement this in the project GUI2. So here's our project, and here is the main file for it. Notice that we come down here into the main method, which is where it starts, and this starts by creating an instance of the GUI2 class, which is this class. Then as soon as it's created that, it calls the go method on that instance. What the go method does is to interact with these 3 private member variables, a JFrame, a JButton, and a JText area. It creates the JFrame and gives it the name GUI components. It sets the layout on the frame to be a 2-row, 1-column grid. Then it creates a JButton with the label click me and a JText area which represents multiple lines of editable text, and it sets up initial text within there to say edit this. Then it adds the button to the frame and adds the text to the frame, sets our close operation so that we'll actually quit the program when we click on the close button, sets the bounds and makes it visible. So let's just run that. And we see that we get pretty much what we would expect. There's our button. There is our editable text field. We can type into this thing and it has multiple lines. We can resize things and we can click on the button, though it doesn't do anything yet. Okay, so we'll close that up. Now to add behavior to this button, we must create a class that is the shape, for the want of a better word, that the button expects. This is a bit like saying that when you have a blocked drain, you call a plumber. You have certain expectations about instructions you can give to the plumber. You'd be really surprised if you said, please Mr. Plumber, unblock this drain, and the person you'd hired said, I don't do that. Similarly, the button is going to have expectations about the code we give to it. Specifically, it expects to be able to say, in a formalized way, I just got clicked. We're going to do this for the sake of convenience in the same source file. Now normally this is not a great idea, but it allows us to put all the code in one place, which makes it easier to understand. Actually, the only way Java allows this is if we make the class not public. That's a bit odd in itself. So just remember this is a learning exercise and not something that you should do as a rule. We'll call the class myButtonHandler. So I'm going to scroll up here and we'll create this right here. And it needs to implement this interface action listener because that is what the button expects. So we will also need the import for the action listener. And then we'll notice that as soon as we've defined the action listener interface, the compiler is now saying that my button handler doesn't actually implement the methods that we've said it will implement. So if we click on here and click the implement all abstract methods, you'll see that NetBeans will fill in the blanks for us. It says that to be an action listener, you must have this method, action performed, returns void, takes an action event as its argument, because that is the method that button expects to call when it's been clicked. Now, the way NetBeans has created this method, it's going to explode in our faces if we try to use it, because it has this exception in there saying we haven't written the code yet. So we'll replace that with something slightly more useful. So here we say, just print out a message, button was clicked. So let's just print out a message, button was clicked. Now the next thing we need to do is to arrange that the button can call this method when it gets clicked. We do this by creating an instance of this handler class and passing it to a method in the button called addActionListener. So we'll come down here, and just after we have created the button, we will say the button addActionListener new myButtonHandler. We create the instance of this class and pass it to the button and tell it to add this as a listener for actions. That means that when the button gets clicked, it will call this object dot action performed to tell it that the click has occurred. So let's save this and run it. If we click on the button, you see that we now get the message in this console down here, the button was clicked. That looks like a good first step. Of course, we might want to do something more imaginative than just printing a message on a console. Let's assume that we want to update the text in the text area. We would need to call a method called append in the text area to do that. But we don't have a reference to the text area in our handler. Now, we could modify the listener so that we pass it a reference to the text area when we construct it. In other words, add something here so that we have a way to store the reference to the text area in here, and then when we construct it, new myButtonHandler and provide the text as an argument. But that's a bit cumbersome, and while it would work perfectly well, remember that a private variable in an object is accessible between the curly braces that enclose it. In other words, the text is visible from this opening curly brace right the way down to here. Now it turns out that we can actually create one class inside another class. We can even create one inside a method. So let's take this class, we'll cut it out of there, clean that up a little, and then we'll move that inside here. We'll reformat it. Notice no complaints. It looks a little odd for sure. We've got a class defined inside the go method. Let's save it and run it. And sure enough, when we click it, button still prints the message it was clicked. So what we can do now, in this method, we can refer to this variable the text. And that means that we can say the text dot append button clicked at plus new date. So we'll put a date and timestamp on the end of there. Put a semicolon on. We'll also put a new line character that's represented by \n into that, and we need an import for java.util.date. So now if we save that and run it, let's make the window a little bigger, and each time we click it, we'll see that we get a message appended to the text that says button clicked at and the timestamp. Now there's actually another shortcut you'll often see experienced Java programmers use in this kind of situation. Notice that there's really only one use for this particular class, the myButtonHandler class. Well, the chances are that we only ever create an instance of it right here and immediately attach it to the button. Java actually allows us to skip giving this class a name. So watch what happens here. I'm going to delete this constructor here and put some blank space so that the whole of this area is the space for the parameter to the addActionListener method. I'm going to change this class so that instead of saying class myButtonHandler implements ActionListener, I'm going to say new ActionListener and put parentheses on the end of it. And then I'm going to cut this out of here and embed it in here. Now it wants a little reformatting. We clean it up, but now what we have is we have this new ActionListener parentheses, and there's the opening parentheses, there's the matching closing parentheses, and we're actually creating an instance of an unnamed class that implements ActionListener right here as the immediate argument to this method. Let's save that and run it. And you'll see still that when we click on it, it behaves just as it did before. So in effect, what I did was I moved the class definition into the method argument. I dropped its name completely and just said new ActionListener. It means the same thing, but this is called an anonymous inner class. You don't actually have to use this form if you don't want to, but you will have to be able to read it, as it's really popular with Java programmers because it's brief. As a final note, you might be wondering where all these methods, interfaces, and so forth are coming from. Well, after a while, you'll start to know some of them just because you use them a lot. But mostly they're in the documentation. Let's take a look. Here's the documentation, and in this top left corner, remember, we have all the packages. Well, it turns out that the swing package happens to be in a javax.swing package. So as we scroll down here, there we find javax.swing. Here is the javax.swing package as a whole, all the classes, all the interfaces, and so forth. And this is the general top-level documentation for javax.swing. So, for example, in here we'll find lots of things like a JLabel, a JList, a JList drop location, a JMenu, a JMenu bar. Many of these look as though you could probably make a reasonable guess as to what they do. A JRadio button, a progress bar, and so forth. Well, if we look at the JButton, we get the documentation over here. If we scroll down to the constructors, you'll see that we can create a JButton and we can give it a string text argument, and it creates that button with the specified text. So that becomes the text of the button. Also in this JButton class, we will see that we can find the addActionListener method. This is actually inherited from a parent class abstractButton. In other words, there are multiple kinds of buttons. Radio buttons and checkboxes are types of button, for example. And if we look at that, that one tells us that it adds the ActionListener to the button. We can click on the ActionListener argument type and discover that the ActionListener declares the actionPerformed method and tells it that it will get an action event when it's invoked. Let's take a quick look at the action event. Here you see that inside an action event, we have a number of methods. We can get when to find out the time that this action occurred. We can get modifiers to find out if there were keys held down during the occurrence of this action, and so forth. Similarly, if we come across back to our main list of classes, we can find that we come across the JFrame. And the JFrame will tell us things that we can do with that. So we can construct one and give it a title string. We'll also see that we can have a setBounds method, which is actually inherited from a parent class, a window. There's a couple of those, but if we click on this one, we'll see there's a setBounds method that takes an x, y, and a width and a height. So these are the kinds of things that we would do to work out how to do something that we've not seen before. A little bit of imagination and a little bit of scrolling up and down this documentation will allow us usually to work out most of the things we want. So, this lesson looked at adding behavior to a user interface, and along the way we took a look at how we can define classes inside other classes, and in particular at this curiosity called the anonymous inner class. In this lesson, we'll look at some more layout features. They're still quite basic, but they serve well in many applications. We'll also look quickly at a feature of NetBeans that might be useful for you in creating layouts. This example code is in the project GUI Layout. Notice that in our main method, we create an instance of the enclosing class GUI Layout and then call its Go method. The Go method simply constructs another class, BorderEX, and calls its Show method. Let's have a look at BorderEX. BorderEX defines a number of private fields, one of which is the frame. The frame is created as a JFrame with the label text border layout. Then it creates 5 buttons named North button, South button, East button, West button, and Center button, and creates those buttons with text North, South, East, West, and Center. The Show method sets the layout to be a border layout. And then each of the buttons is added in turn to the JFrame with what's called a constraint object. The constraint object, in this case borderlayout.north and subsequently borderlayout.south, east, west, and center respectively, is used by the layout manager to help guide it as to where a component should be positioned. You'll see what these mean in just a moment when we run the code. Then we call this method pack on the frame. What pack does is to tell the frame to ask the layout manager to work out the natural size and position that best suits the contents that have been put into this frame. Then we tell the frame to make itself visible, and we should see something. So let's go back to our main program and we'll run this. Here is the resulting output. Notice that the button labeled North is at the top. The one labeled South is at the bottom end. West is off to the left side, East is off to the right side, and Center is in the middle. One of the things that's important about a layout manager is not just how it initially positions those components, but also how the available size is allocated to them as you resize the window. So if I grab the corner of this and make it grow, notice that the components at the north and south retain their natural height. The components at the west and the east's elements retain their natural widths. But the north and south components grow and shrink horizontally, while the east and west components grow and shrink vertically. And the one in the center gets all the rest of the space. If you leave any of these components out, the area allocated to them disappears down to nothing. So if you just had north, west, and center, you could set something up that looks quite reasonably like a menu bar across here, a navigation bar down here, and then a workspace in the middle. So that's the border layout. We're going to kill that from here. The next layout is the grid layout. This one sets up a regular grid of components with a specified number of rows and columns. In this case, we create the layout for it using the grid layout, and we specify that it has 3 rows and 2 columns. The frame that we put it into is labeled with the title Grid Layout. Then we create an array of 6 buttons labeled button 1, 2, 3, 4, 5, and 6. We use a loop to add all the buttons into the frame. Notice there's no constraint objects in this. The order we add them to the frame will determine the position that they adopt. Then we pack it again and set it visible. Let's add this to our main program. Save that and run it. And this time we notice that we have the grid equally divides the vertical space into 3 subdivisions, and the horizontal width of the thing is divided into the 2 columns that we asked for. So that one's our grid layout. Again, we'll close this. The final layout to look at is called the flow layout. The flow layout simply lays out the components in the container like words in a text editor. So what we'll find is that these buttons are laid from left to right and just spread out horizontally. As we resize the frame, then we'll get some of those buttons being pushed down onto second and third lines. So in this case, we create our frame, we give it its label, we create an array of buttons, we give them different names. You'll notice this one is designed so that it's extra wide and this one is a little narrower. We create the frame and add the layout manager to it. This is the flow layout. And then we add each of the buttons to the frame. We pack it, we set it visible again. So let's add this one to our main program and have a look at what that does. We'll edit the code, save the file, and run it again. And here is the interesting one this time. Notice the buttons are just laid out left to right like words in a text editor. If I make this layout bigger, it doesn't do anything useful with the extra space. But if I make it smaller, then the moment those buttons don't fit, it moves them round onto a new line, just like word wrapping on a text editor would. So that's the flow layout. The next thing we need to do is to look at a builder tool that allows us to build graphical user interfaces using a drag and drop technique. This is more or less unique to NetBeans, but what we're going to do is we're going to right click on our package, say new, and then see here it says JFrame form. And I'm going to call this builder layout. Click finish. And if I double click on this tab, I can get the benefit of some extra space. Now what I have here is a workspace, and over on this side I have a menu of all the components that I can add to my JFrame. So I could take, for example, a label and drag it across. As I do so, you'll notice that it offers me the chance to snap it to certain positions. So now it's snapped to the top left corner with a little bit of border space around it, and I can change its text by double clicking on it and then adding label text. Hit enter, we'll take that. Then I could grab a button, for example. There's a button. Drag that across, and I can arrange, notice the baseline under the text, that will line up those text baselines so they look properly lined up together. If I drop that there and then grab this right hand edge, I can tell the system I want the right hand edge to attach itself to the right hand edge of the layout. Then I might grab, for example, a text area, move that across, and I can stick that up tight in the top left area underneath everything else, and then bring its bottom right hand edge down here and get it to click in there. There's a nice feature of this tool that if I click on this button, preview the design, it will actually build it right there and then, and I can see what it looks like, and I can resize it and check that the dynamic behavior I've got is what I was hoping for. Well, let's close that. Something else you'll want to see is that if you click on the source button, you can actually see the source code that this is generating. So you can interact with it, for example, and add your listeners as you need to. Well, let's double click this again, make it shrink back to its normal size. What I now need to do is to add this to my main program. So if I come across to GUI layout.java, I can now come in here and I can create an instance of this class, new builder layout, and then I can call the set visible true on it and put the semicolon in, save everything, click on here, and then if I run this one, you should see that in addition to the other three windows that were created manually, we have this new window. We can click on the button, there's nothing attached to it, we can type in the editor field and so forth. This one by default, if we click on the close button, that one by default will shut down the VM. NetBeans, by the way, uses a special layout manager called the group layout. It's very powerful. You can use it yourself at a source code level. Its original intent was to support drag and drop builder tools like the one we've just looked at. In addition to that, there are several other layout managers you might come across, including something called the grid bag layout and the box layout. So in this lesson, we've introduced the border, grid, and flow layouts, and had a look at how NetBeans' graphical builder tool might help you with more complex layouts. In this lesson, we're going to look at how to interact with GUI components in general. It turns out that GUI systems, including Swing, must run in a single-threaded way. Since Java is multi-threaded, this won't actually happen by default. But there's an easy utility to allow us to do our interactions correctly. Additionally, if we want our UI to remain responsive, we must avoid performing long-winded processing in our event handlers. there's another utility to help us with that. Let's take a look at this example in the project Swing Updates. We have the same kind of configuration we've seen a number of times before. We create an instance of the enclosing class and call a method on it called Go. Here's the Go method, so this is where the work happens. We create a JFrame, we set a layout, which is going to be a grid layout with 2 rows and 1 column. And then we create a button and a text area. This time we're creating a scroll pane for the text area. So this scroll pane will allow us to scroll the text area around if there's more text in it that can be shown in the window. We add a listener to the button. So when the button gets clicked, we should print out the message, "Button was clicked." Then we add the button to the JFrame and the scroller to the JFrame, set the close operation so it will actually shut the system down, set the size and boundary of the JFrame and make it visible. So if we run this, we can see that when we click on the button, it prints the message, "Button was clicked," down here. Although it's not obvious, this program has 2 threads running concurrently. There's the normal thread, that's the one that runs our main method, but there's another thread that is created to handle the user interface. That other thread handles our mouse and keyboard interactions, like the click, along with some other related UI behaviors. We can demonstrate this by asking the threads to tell us their names. We'll add some code to the main thread just after it has created and launched the user interface. So we'll put this just here. This one says print out main thread name is, and then this code here goes and says whatever thread is running me, get a hold of the object that describes it, and then get its name as text and print it out. The other thing we'll want to do is each time the mouse button is clicked, we'll add some code here. So this is going to be essentially the same kind of code, but this time it prints out user interface thread name is and prints out the name of the thread. Let's save that and run it. Here you can see main thread name is main. When we click on the button, however, it says button was clicked, UI thread name is AWT event queue 0. Let's close this one down. So you can see from the different thread names that we really do have 2 different threads working. Well, why should we care? Well, suppose we wanted the main thread to write text into the text area at intervals. We would probably try something like this. Let's put some code just in here. This goes into an infinite loop and it uses this method thread sleep. And what that will do is to suspend the thread for, in this case, 2000 milliseconds or 2 seconds, and then continue by calling the append method on the text area along with the date stamp. The try catch around this is because the thread sleep method actually is declared that it might throw an exception, and we're obliged to handle it. So if we save this and run it, we can see that at 2-second intervals, the main thread is updating our user interface component here and is writing messages into that. So what's the problem? That seems easy enough. Well, the problem is that it's not safe to interact with GUI components from any thread other than the event thread. That's the one that handles the button click. The odd thing is that this works almost all of the time, so you could easily fall into the trap of doing it this way. What we actually need to do is to ask the event thread to do the work of interacting with the GUI components for us. We do this by wrapping the work up in a special package called a runnable. Runnable is an interface, and we almost always use an anonymous inner class to do this. In a runnable, the run method is the place where we put the work that we need to do interacting with the graphical user interface components. So what we need to do is to embed this line, the text.append, inside the run method of a runnable. Let's go ahead and create a new runnable, and we'll create the basics of an anonymous inner class. And if we click on here, we can implement all the abstract methods. So there it's created an unimplemented body for our method. We want to move the append method call inside there. Now that we've got this runnable,
that defines our work or our job description if you like, we can pass that to the event thread using the swing utilities class. This class provides a method called invokeLater. So we will say swing utilities dot invokeLater, and then we provide our runnable as the argument to that, and we need an import for it. So now what we're doing is we're telling this utilities class that at its convenience, and it won't wait too long, we want it to use the event thread to run this code, the code defined by the run method in this runnable. So if we save that and run it, we notice that we still get our updates and they're still at 2-second intervals. We can still click on the button. So it looks like nothing has changed. But the important thing is now this code is safe. The problem really is you rather have to take it on trust that this is the right way to interact with GUI components and that what we did before was wrong. The wrong way won't fail every time. In fact, it won't fail at all unless the event thread and the other thread happen to interact with the GUI at the same time. Even then, there's a fair chance you'll get lucky and it'll just work. So remember, you must interact with GUI components using this approach unless you're already using the event thread. So how would you know you're using the event thread? Well, generally, if you're in an event handler, one of the callback handlers that you added to a component, like this button handler that we have here, then you're in the event thread. Also, if you've been invoked using the swing utilities invokeLater method, then you're in the event thread. If you're unsure, you can always print out the name just to check. There's another rule regarding these threads. We mustn't do long-winded processing, for example database searches, using the event thread. The problem is that if you do, you will prevent the user interface from doing anything else until you're finished. This could happen if we were to include this sleep statement here in this run method. But a more realistic situation is to have an extensive computation in an event handler. So our event handler for the button is up here in this actionPerformed method. So let's add a lot of computation to that. What we'll do just after we've printed out the name of the thread, we'll add a loop. We're going to say starting so we can see that it's doing something, and then we're going to create a very large number, 50 million date objects. I'm going to abandon them, they're not going to do anything useful, but it'll take the system a little time to achieve that. So if we save this and run it, notice what happens when we click the button. So at the moment everything's working, we're getting this output, we can click that, but then I can't do anything. It says starting, and for as long as it hasn't finished, the system basically hangs up. Then when it finishes, see it said done now, then things come back to life. But each time I click on this, I can't resize the window, I can't type characters in this field, and everything basically hangs up. So let's close this down. And then the question is, what am I going to do to actually make this work properly? Well, what we have to do is to pass this work off to another thread. This is similar to passing the update behavior to the AWT thread, the event thread. But we're doing this the other way around now. We're in the AWT thread and we need to find some other thread that we can use to handle the work. Fortunately, there's an easy way to do this. There's another utility called the swing worker. This one actually uses a slightly different packaging mechanism from the runnable we used last time. Let's bring a piece of code in that does this in its simplest form. So here is our long-winded code. I'm going to embed that inside this swing worker. So here we construct this anonymous inner class. It's a subclass of the swing worker class. What we've done is simply put our behavior in this doInBackground method. That's kind of the same as putting the behavior in the run method previously. Now the doInBackground method is actually declared as returning an object, but we're not using that aspect of it, so we can simply return null. So what's going to happen when we come into our actionPerformed method, we'll print this message and this message in the event thread, but then we will set this new job up
so that another thread created for us by the Swing infrastructure will execute all this code. I'm actually going to reduce the time that this blocks for, because otherwise it gets a little boring. And then we'll click on this guy and run it. So let's bring this down here so we can see what's happening. We're still getting our updates. When we click there, we see starting, and then a second or so later we see done. If I click this several times, we see lots of startings, but I can still move this, and then we see a lot of dones. So the nice thing is that all that work is being done in another thread. It's actually not the main thread, neither is it the event thread. The important thing is that it's not the event thread. Here's one last thought. What do you suppose would happen if you wanted to update the graphical user interface when this work done in here was completed? Yeah, that's right. This is not the event thread, so you can't do it directly here. You'd have to use the Swing utility invoke later behavior that we looked at earlier. This can all seem a bit messy until you get used to it, but you do get used to it, and then it's not so weird. By the way, this behavior is not unique to Swing. Pretty much every GUI tool around works this way. It's just kind of a law of physics that you can't have concurrent access to a graphical user interface and expect things to work well. So this lesson has looked at the threads that are alive when a GUI program is running, and investigated the rules that constrain our interactions with GUI components, and the key utility classes that we can use to make usable GUIs while adhering to those rules.
Congratulations, you're almost there. In this part of the course, we're going to actually create a working project. The project is going to be a basic network chat system that allows you to send messages from one person to another across two machines if you want to. To do this, of course, we're going to need to put all the pieces we've already worked on together. We're going to need to lay out a graphical user interface. We're going to need to attach behavior to that graphical user interface so that you can send a message. The other side of the system is going to need to be able to receive that message too, of course. To make this happen, we're going to find that attached to the back of our user interface, we're going to be performing I/O operations. And with that, of course, we're also going to have to address the possibility of exceptions, problems arising when the system is running. We're going to discover something very pleasant about the way that network handling is done. We're going to have to introduce network handling, but you're going to find that in Java it's really easy because you already know how to do general I/O, and you might remember that I mentioned that there was a pleasant surprise waiting for you in terms of generalization when it came to I/O operations. Well, this is that pleasant surprise. The way that network I/O is handled is the same generalization as was used for handling the keyboard and the screen and for file I/O. The only thing that's a little different is the way you actually set things up to make the connection in the first place. And we'll illustrate that as we build this project because we'll start testing it just using regular keyboard and screen type I/O to actually build the system up. And then, not exactly for the flick of a switch, but with very little intervention, we'll be able to change it so that our system works across a network. So by the time you finish this part, you'll be done. We'll have shown you everything that we wanted to show you that should allow you to go out there and build real Java programs with real algorithms, real code, real object orientation, and real user interfaces, and basically you're a Java programmer now. Congratulations.
In this chapter, we're going to build a complete project for a simple chat program. To do this, we'll first need to create a user interface, and we'll need to do a little work with Java's network library. Like many things in good object-oriented systems, the network library is largely a specialization of the I/O library. So although we've not looked at it before, it shouldn't be too hard to get to grips with. This lesson will look at the first part of the problem, laying out the graphical user interface. We're going to need two components in the graphical user interface. One will be a text area that contains the conversation, and that should probably be scrollable to allow for long conversations. We'll also need a text field that is used to enter the next comment that that particular participant wants to make. This UI will be used by both participants. So let's start by building this UI. We'll create our project, and we'll call this Chat Client.
I'm going to call the main class TestIt. I'm going to put it in the package chat. The reason I'm going to call it TestIt is that for the time being, this main program is just going to be a way of testing our work in progress. It won't actually be part of the finished product. So we'll hit finish on that. So step one is going to be to create the chat window layout. We'll start by creating a new class and call that one Chat UI. So new Java class Chat UI. This class is going to need to create a JFrame, a JText area, that's the multi-line text device, a JText field, which is the single line one that will be used for input. And we're also probably going to want to have a scroll pane, and we'll need some private variables for these. So we'll start there. We'll create the variables. And you'll notice that as soon as we do that, we get the complaints. We need some imports. So we'll arrange for the imports. Remember that we can achieve from source fix imports, or we can hit Command-Shift-I or Alt-Shift-I in a Windows platform. So there are our variables. Now the next thing is we need to think about how we might construct this. Obviously we'll have to have a constructor, and the JFrame will probably want a title bar. Now because we're planning to use this GUI for both ends of the conversation, we'll probably want to make that title bar a parameter to the constructor. So let's start creating our constructor. We'll assume that we're going to provide a title, and we'll call it title. The first thing we'll do is to create our JFrame, and we'll set the default close operation on that. Next, we'll create our chat text, which will be our JText area. So that's the multi-line display. We'll add that to our scroll pane. So in this case, we create the scroll pane and provide the chat text, the JText area, as the argument to it. And then we will add the scroll pane to the frame. We need an import for the border layout. Now notice this time we didn't actually explicitly set a border layout on the JFrame. As the comment foreshadowed, it turns out that actually the JFrame already has a border layout as its default layout manager, so we don't actually have to worry about that. Next we need to add the single line text field, which we're calling entry text, and we're going to put that into the frame at the south position. Then finally we will set the boundary of the frame. I'm going to do this explicitly because an empty text area doesn't really try to take up much space. We want it to have a sensible amount of size. So we'll set the bounds to 2020 for our offset, so it'll appear up in the top left corner. We'll give it a width and height of 300, and we'll set it visible. Do you remember the rule about not interacting with GUI components except in the event thread? Well, up to the point where we set the frame as visible, there's no event thread in this case. But there are some situations where that wouldn't be true. Consequently, it's actually good and standard practice to use the invoke later functionality to perform the building of our layout. So we're going to wrap this whole thing in a call to invoke later. I'm going to add this at the front of our code. So there's our swing utilities. We'll have an import for that. There's our invoke later. We're declaring the new runnable. There's the body of the run method for the runnable, and there's the emptiness. So what we'll actually do is we will copy this lot and we'll move it inside that run method, and we will go Control-Shift-F for format. If you ever find you can't remember that, you can right click on that pane and find format down here, and then it will remind you what the shortcut key is. We'll clean up a few of these spare blank lines. And now we have the body of our construction going on in the AWT event thread. So everything is now completely safe. Unfortunately, you notice that we now have a complaint about title. If we hover over that error, it says local variable accessed from inner class needs to be declared final. That's something new. Now, for reasons that we're not going to get into in this lesson, we actually have to mark this title parameter here where it's declared as final. That means that that variable can never be changed. Well, that's fine because we don't want to change it.
But the important thing is it also allows us access to that field from inside our inner class. So now you can see it's happy. Okay, so let's test this from the testit main file. What we'll do, we'll put in here simple call to construct this thing and give it a title field. If we save that, and I'm going to right click and do run file, there's our layout, and we can type in there, and actually we can also type in here, which we didn't really expect to be able to do. I don't want to be able to do that, but let's kill this for a moment. And if we take a quick look at the documentation for JText area, so in the swing package, JText area, you'll notice that under JText component, the methods inherited for that, there is a method called setEditable. That sounds like that might do what we need it to do. Notice while we're at it, there are also getText methods. So we might want those later on as well, so we'll keep those in mind. If we click on setEditable, we'll see that setEditable takes a Boolean value, and that will allow us to indicate whether this text component should be editable or not. So that will probably do what we need it to. So let's go back to our chat UI, and we will find our chat text, and we will set editable false on that. Chat text.setEditable false. We save that, run this again. Now we should find that we can't type in there. I'm bashing keys and nothing's happening, but we can still type in there. So that looks rather better. So there we have it. In this lesson, we've built a graphical user interface that lays out the components we'll need for our chat tool project. The next step will be to arrange for this to connect to I/O channels so that we can send our messages somewhere and receive messages from somewhere else. This lesson will look at how to enhance our chat GUI so that we can connect it to I/O channels and send a message when the user types in some text and display text that is received from elsewhere. To continue with the principle of taking one step at a time, we're not actually going to do the networking yet. Instead, we'll use the console as the other end of the system. So for our next step, we need to be able to type input into the single line text field, and when we press enter, we want to send that somewhere. Conveniently, it turns out that pressing enter in a single line text field causes an action event just like a button. So let's start by adding something to the text field that responds to us pressing enter. We'll add an action listener using an anonymous inner class. We'll split that line, and then inside there we will add a new action listener, and we'll split that line. And notice that NetBeans is complaining. First we need to import action listener, and then we need to implement the abstract methods. Now we'll reformat with Control-Shift-F. That makes it a little bit more readable. So now we have entry text add action listener. We immediately add the action listener as an anonymous inner class, and the implementation will go in here. Now at the moment this is throwing an exception, which isn't terribly helpful. We'll delete that, and then let's think about the behavior we want. What we actually want to do is to grab the contents of the text field, write it to the output, and then it would be nice to blank out the text field so that we're ready for the user to provide the next entry. We can do that by calling the method getText on the entry text object and then sending that initially to the system output. Then we can set the text on the entry text and set it to null. Let's save that. We'll go back to our test program and see what it does. So if we type in here, we see that it does in fact generate the output here. That looks like a good start. Now we don't really want to send the output to the console in the long run. We want to send it over a network. Conveniently, we're going to find that outputting to a network connection is essentially the same as outputting to any other output stream. So if we modify the constructor to take a writer as a parameter, let's use that instead of the console as our destination. then for now we can still test it using the console anyway. So let's go to our chat client again, and we will add a second parameter. We need an import for writer, a second parameter called output of type writer, and guess what? We've labeled it final as well. You've probably guessed correctly, we're going to be using that inside our inner class, and therefore it needs to be labeled in that way. Let's change the behavior of our action event handler. Instead of sending the line that we've just read to the console using systemoutprintln, which is specific to the console, now we're going to change that to say output.write. We're going to take the line and we're going to append to it a new line character. We will also add a second line that says output.flush. The reason we're doing that is that not all I/O gets written immediately at the time when we make the statement to send it. With console I/O, output will be sent immediately because the system knows that that's why we're sending it. We want someone to read it. But this output.flush statement will force the system to send our message to the output. Without it, it's actually likely to sit in a buffer going nowhere, and we'll be wondering why our program doesn't work. Let's also add something that outputs this message to our chat window. Here let's say chat text append, and then we'll prefix the message with me : so that we know that this is our message. We'll embed the line in there and put a new line on the end of it. So now when we send something, it should show up in our output window. Well, of course, rather inconveniently, we can see some errors have shown up here. It turns out that output.write and output.flush, those methods output and flush, are declared as potentially throwing I/O exceptions, and we have to handle those. We first need to think about what this might mean. It seems most likely that if a network connection were broken, then an attempt to write to it would have to fail. So we'll work on that basis. We'll put a message in the console indicating that the other party hung up on us. That's not perhaps as full or robust a response as it might be to this situation, but it seems like a pretty good start. So we'll add, just above here, a try block, and then after here, we'll add our catch block. We need an import for I/O exception, and we will reformat that. So now, if these lines fail, either of them, we'll end up catching an exception here, and then what we'll do, we'll put a message that says the other party hung up in our chat log window. So let's test that. Come across here, we'll save this. Now before we can test that, we need to modify our test code, because now of course we need to provide a second argument to the constructor that is the writer that we want our GUI to write to. We need a writer, not an output stream, and that writer is going to be connected to the system.out channel. So we can simply add in here a new output stream writer, for which we need an import, and connected to system.out. So we'll save that, and then let's run it. So there's our window. Let's bring it down here a little bit. When we type in here, we still get the output showing up here. But the important thing is we have now generalized the chat GUI so that instead of always writing to system out, it writes to the writer that we give it. The next thing we need to be able to do is to collect input from somewhere else and send it to the chat window. We can cheat again and test this using the console, at least initially. But first, let's consider that we will not be getting messages from the network via the GUI. So there are not going to be GUI events to handle this. We'll be looking for these network messages in the main thread, and we can't write directly to the GUI from that thread. So we're going to need to add a method to our ChatUI class that will allow us to safely update the chat window with a new message. Let's put that just after this method, like that. So here we've declared a method, append text. We've said that it's going to take a message as its argument. Oh look, this one's labeled final as well. You can probably guess why. Sure enough, inside here, we use the swing utilities invoke later, which means now we're going to create this anonymous inner class for our runnable, and the run method simply says chat text.append, and then we say they
indicating that it's the other party that sent this message, put the message in, and put a new line on it so that our messages don't all run together. So this should be getting fairly familiar now. Now we can call this from our test method when we've read something from the console. Let's go across there. So the first thing we're going to need to do is to actually get a hold of the system input, and we'll need some imports for these things. So we connect an input stream reader to it and a buffered reader to that. Remember that the buffered reader is the one that gives us the convenient read line method. We're also going to need to keep a handle on this chat UI object so that we can call the append text method on it. So now we have a variable that will refer to that for later use. Next thing we need is a loop that reads from the keyboard and calls append text every time it has a new line to update. Let's put that here. Of course, this might throw exceptions. Since this is the test, we'll just cheat with this and declare that the main method might break. So in here we'll say throws throwable. We'll save that, and then we'll run that and see how we're doing. Now, of course, we're going to need to resize these windows to see what's happening. We'll bring this down about there-ish, move it over there. Now we can get both of these side by side, and we should find that when we type in here, that shows up in here, and when we type in here, it shows up in there. So now our GUI window is capable of sending messages from here to a specified writer and receiving messages and updating its display from the main thread. So there we have it. In this lesson, we've modified our GUI so that it connects to a writer and sends updates to that writer based on the user's input, and simultaneously can be updated from another thread as the result of input messages. Our next step will be to connect this to the network instead of to the keyboard. In this lesson, we'll look at attaching the Chat UI user interface to the network. To do this, we need to understand a little about the TCP/IP network system and how the Java libraries interact with it. At its simplest level, the network is quite a bit like a phone system. In this situation, one party is waiting for the phone to ring, and the other does the ringing. In the network, the program that is waiting for the phone to ring is called the server, while the one that does the ringing is called the client. Let's take a look at the code. Here is the server code, and you'll see that the first thing it does is to create this object called a server socket, and its parameter for the constructor is a number. This is called a port number. This is a lot like the extension number in an office telephone system. The client, by contrast, makes a connection to what amounts to a phone number and the extension. The phone number in general is actually going to be a DNS name, so for example something .com. However, our example, we're going to want to have both the client and the server connecting on the same machine so that we can run everything locally. And it turns out that 127.0.0.1 is a magic number which says connect back to your own host. It's called localhost in some systems, but that's not very reliable in Windows. So here on the client, when we create this socket, we are effectively making a phone call to our own machine, but connecting to the extension 1234. On the other side of that connection, here we tell this program to listen to the extension 1234. We don't have to specify a phone number because obviously we're already inside the building. So we're listening for our own phone to ring. In the server, once we have set up this server socket, we then have to effectively tell the receptionist to answer calls. And this ss.accept call, the accept call on the server socket, does that. When ss.accept returns, it returns an object of type socket to us. And a socket is very much like the telephone handset.
If we look at the client for a moment, you'll see that we actually created a socket directly by connecting it to a phone number and an extension. So now, in fact, both the client and the server are connected using this exact same object type called socket. And a socket's essential job is to embody an output stream that we can send data down and an input stream that we can read data from. Of course, we're familiar with the mechanisms that Java uses for reading and writing data on an I/O channel. So it shouldn't be a big surprise to see that the next thing we do is to create a variable called input of type buffered reader. The buffered reader is connected to an input stream reader. Remember that converts 8-bit bytes into 16-bit characters, and it in turn gets its character stream from the socket. So s.getInputStream. The getInputStream method on a socket gets hold of an 8-bit byte stream that we can read characters from. Those characters are the characters that were sent from the other side of the network. We do the same thing in the server side. Exactly the same thing, because we're dealing with a socket again. If we look back at the client, the next thing we do is we get the output channel of our socket. That is s.getOutputStream. We wrap an output stream writer around that to allow us to write 16-bit characters to it, and the same happens on the server side. Exactly the same code. The client creates the chat UI window with the label client end and a connection to the output writer. It then goes around reading lines from the input. Those will be messages received across the network, and for as long as we are getting messages, it appends those messages to the text area in the chat UI itself. When it reads a null, the null indicates that this socket has been closed, and that will cause it to drop out of the loop, and then it will send the message to our text area that says connection lost. Unsurprisingly, the exact same thing happens on the server side. And that's all there is to getting basic networking going. So let's run this. We'll want to start the server first, because remember, it's the server's job to be listening for connections. If the server isn't listening when the client makes the call, the client will fail because it gets no response. So we'll start by running this one, and we will right-click and run file. Notice that we actually have 3 executable programs. We have our test program, and then the server and the client pieces. So we must use the run file option rather than hitting this green button, because this green button is going to start the test piece. We don't need that. So now we'll select the chat client and we'll right-click, run file. So this is going to make the phone call, and as it does, the server is able to respond. It pops its user interface up, so does the client. Now if we type things into the client side, the message appears for me on my own log and appears on the server end. And if we type in the server end, similarly the messages go back the other way. So problem solved. We now have these 2 instances of our chat UI connected to the network connecting them to each other. In this example, both ends of the network are running on the same machine. But if we close these, all you would need to do to make this work across machines is for one machine to act as the server. So you'll just run this program exactly as it is, unchanged. And then on the other machine, you'll run this program and you'll modify it so that this field contains either the IP address of the machine. If you're running a home network, that's likely to be something like 192.168.something.something, but you'll have to look at your own network to work that out. Or possibly a DNS name. So mymachine.com or something of that sort, depending on how your network is configured. And there we have it. In this lesson, we have put together our chat UI GUI elements with a network socket and created a real network client and server program pair so that we were able to send simple text messages between 2 different running Java programs.